When we look up into the cosmos, we imagine brilliant islands of light in an ocean of perfect, silent black. We see the beautiful arms of a spiral galaxy, the soft glow of an elliptical one, and in between them, nothing. Just an endless, silent void. We think of the vast distances between galaxies, millions of light years across, as a perfect vacuum, untouched by anything at all. But that's one of the greatest illusions in the entire universe. Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. That seemingly empty space isn't empty. Not even close. It's an active, surprisingly complex place, a cosmic wilderness filled with lost stars and a mysterious, invisible web that holds the secrets to the very structure of our universe. What if I told you that this emptiness is where the real story of the cosmos is written? What if the void isn't a void at all, but a sprawling ecosystem that connects everything we can see and everything we can't? Tonight, we're journeying into that great, dark expanse to uncover the secrets of the space between galaxies. The grand illusion of emptiness. For centuries, our picture of the universe was a simple connect the dots of its brightest points of light. The space in between was just that space, a backdrop. It was so mind-bendingly vast that it hardly seemed worth thinking about. A single photon of light can travel for millions of years just to cross the gap from one galaxy to another. To our eyes, and for a long time to our telescopes, these intergalactic regions were the very definition of nothing. And our early models of the universe backed this up. Galaxies were like ships on a calm, dark sea, each one isolated by immense, unbridgeable distances. The universe was a collection of things, and the space was just the canvas they were sitting on. This felt right. It was intuitive. When you see a deep sky photograph of a galaxy like Andromeda, your eye is drawn to its swirling light. The blackness around it just makes it look prettier. It's the frame, not the painting. But science has a wonderful habit of starting where intuition ends. The first hint that this perfect emptiness was a lie didn't come from what astronomers saw, but from what they couldn't explain. It was a mystery born from movement. In the 1930s, an astronomer named Fritz Zwicky was studying the Coma cluster of galaxies. He watched how the galaxies were moving, and he found something that just didn't make sense. They were moving way too fast. Based on all the visible stuff, all the stars, gas, and dust he could count, there shouldn't have been nearly enough gravity to hold the cluster together. The galaxies should have flown apart, each one spinning off into the void. The only way the cluster could exist was if there was a huge amount of invisible mass providing the extra gravitational glue to hold it all together. Zwicky called this mysterious stuff dark matter. It was a wild idea, and for decades, it was pushed to the fringes of science. But it was the first real clue that the universe was hiding something big from us. Zwicky's math suggested this dark matter wasn't just in the galaxies, but also between them, filling the space everyone thought was empty. Suddenly, the void had weight. It had influence. The grand illusion of emptiness was starting to crack. The first clues of a hidden architecture. Zwicky's dark matter was a ghost in the machine, an idea that made the math work. For a long time, there was no way to prove it was real. But other clues started popping up, all hinting that the space between galaxies was far from empty. As telescopes got bigger and better, astronomers began mapping the locations of galaxies on a massive scale. And a very strange pattern emerged. If galaxies were just scattered randomly, you'd expect them to be spread out pretty evenly across the sky. But that's not what the great galaxy surveys of the late 20th century, like the Sloan Digital Sky Survey, found. Instead of a random mess, galaxies seemed to be arranged in a colossal, intricate structure. They were grouped together in long, thread-like filaments and massive, flat sheets, all surrounding enormous, nearly empty bubbles simply called voids. It was as if the universe had a hidden skeleton, and the galaxies were just the brightest points on this invisible framework. They were like cities built along cosmic highways we couldn't see. This discovery was profound. It meant the placement of galaxies wasn't random at all. It was being guided by something much, much bigger. At the same time, cosmological simulations running on supercomputers were trying to build the universe from scratch. These simulations started with the conditions of the early universe, a hot, dense soup that was almost perfectly smooth. Almost. There were tiny, quantum-level differences in density. The simulations showed how gravity, working over billions of years, would grab onto these slightly denser spots and pull in more and more matter. And what grew out of these simulations was breathtaking, a vast, web-like structure. The matter didn't just clump into separate islands. It formed a network of dense filaments and nodes, all connected across enormous, empty voids. The spots where filaments crossed became the gravitational downtowns, where huge clusters of galaxies would later form. The filaments themselves were the channels that funneled matter toward them. The resemblance between the computer-generated cosmic web and the real map of the galaxies was undeniable. It was clear that the galaxies we see are just the luminous tip of a colossal, invisible iceberg. This hidden structure was made mostly of Zwicky's dark matter, forming the skeleton, while all the normal matter, the stuff that makes you, me, and the stars, was draped over it like a thin veil. The space between galaxies wasn't empty, it was the home of the universe's entire architecture. But this led to an even bigger question. If this cosmic web of dark matter and gas was really out there, could we ever actually see it? Dark matter, by its very nature, is invisible, and the normal gas was thought to be so incredibly thin that it would barely give off any light at all. Trying to spot it would be like trying to see a spider's web at night from a mile away. The hunt was on, not just to prove the web existed, but to somehow drag its ghostly shape into the light. Bringing the ghostly web into the light. For years, the cosmic web was a beautiful theory, a marvel in computer simulations that stubbornly refused to show itself. Astronomers knew it had to be there, but how do you see something that's almost completely invisible? The secret, it turned out, wasn't to look for the web itself, but to look for the tiny shadow it casts. The breakthrough came from studying quasars, some of the most distant and brightest objects in the universe. A quasar is the super bright core of a faraway galaxy, powered by a massive black hole gobbling up matter. They are so brilliant they act like cosmic lighthouses, shining a beam of light clear across the universe. This makes them the perfect tool for probing the space between them and us. As a quasar's light travels for billions of years, it passes right through the cosmic web. It crosses the voids and, more importantly, it slices through the filaments. While the gas in those filaments is incredibly thin, it's not a perfect vacuum. It has hydrogen atoms, and those atoms absorb light at very specific wavelengths. So, when the quasar's light finally reaches us, it's been changed. Its smooth spectrum is now cut up by a forest of dark lines. Each line in this Lyman alpha forest is like a barcode, the signature of a gas cloud the light passed through on its journey. By carefully reading this cosmic barcode, astronomers could map out all the invisible gas clouds floating in the web. They had found the first, faint signature of the normal matter hiding between galaxies. It proved the filaments were real and filled with thin, cool gas. But seeing a shadow isn't the same as seeing the thing itself. The ultimate prize was to take an actual picture of the web's faint glow. This was a huge challenge. The gas is so spread out it barely emits any light. The trick was to find a place where something else was lighting it up, like a cosmic blacklight. The perfect spot to look was around protoclusters, regions in the early universe where tons of young, bright galaxies were just starting to form. These young galaxies are on fire with the ultraviolet light of newborn stars. Simulations predicted this intense radiation would hit the hydrogen gas in the filaments around them and make it glow. In 2019, a team of astronomers using the MUSE instrument on the Very Large Telescope in Chile did exactly that. They pointed it at a protocluster called SSA-22, more than 10 billion light-years away. The MUSE instrument is an incredible piece of technology. It doesn't just take a photo, it captures a full spectrum of light for every single pixel, creating a 3D data cube of that patch of sky. After extremely long exposures, and by combining the faint light from thousands of different points, they saw it. Faint, glowing threads of hydrogen gas, stretching for millions of light-years, connecting the bright knots of galaxies. It was the first direct image of the cosmic web. The ghost had finally appeared. The picture was stunning. It showed long filaments of gas, some over 3 million light-years long, channeling material into the hungry young galaxies. The web wasn't static, it was a dynamic network of cosmic rivers, feeding the growth of galaxies. And the scale is just impossible to imagine. Our entire Milky Way galaxy would be just a tiny speck inside one of these threads. This discovery was a turning point. It turned the cosmic web from a cool theory into something we could actually see. And with new instruments like the Euclid Space Telescope, which launched in 2023, we're just getting started. Euclid's mission is to create a massive 3D map of the universe, tracing how the cosmic web has evolved over 10 billion years. By mapping the scaffold, we can finally begin to understand the forces that are shaping our universe, including the two biggest mysteries of all, dark matter and dark energy. The discovery of this vast, hidden architecture completely changes how we see the cosmos. What we once thought was a universe of lonely islands is actually a single, interconnected system, woven together by invisible threads. It's a powerful reminder of how much is still hidden right in front of us, just waiting to be found. If you find this journey into the unseen corners of the universe as fascinating as I do, and you want to support more deep dives like this one, an easy way to help is by hitting the subscribe button and turning on notifications. That way, you'll never miss an exploration into the wonders of space. And for those who want to go a step further, our Patreon is a place where you can get access to exclusive content and help us keep making science accessible for everyone. Your support, in any form, is what makes these journeys possible. Now, let's go a little deeper into the void and meet the lonely inhabitants of this cosmic wilderness. The ghostly inhabitants of the void. So, we've unveiled the hidden skeleton of the universe. But what's actually in it? What's lurking in the vast spaces between galaxies? The answer is a realm of cosmic ghosts, a mysterious, ultra-thin soup of superheated gas, and a population of lost, wandering stars. First, the gas. That cosmic barcode from the quasars solved one problem but created another, which became known as the missing baryon problem. Baryons are just the particles that make up normal matter protons and neutrons, the stuff of stars, planets, and us. When cosmologists counted up all the baryons they could see in galaxies and gas clouds, they came up short. By a lot. Somewhere between 40 and 50% of all the normal matter that should exist in the universe was simply missing. For years, the cosmic web was the prime suspect for where it was hiding. Simulations predicted that as gas fell into the web, it would be shock-heated to insane temperatures, creating a thin, hot plasma between 100,000 and 10 million Kelvin. This state of matter is called the warm-hot intergalactic medium, or WIM. Because it's so hot and so incredibly diffuse, we're talking as few as 1 to 10 particles per cubic meter. It emits almost no light and is ridiculously hard to find. But it's not totally invisible. At these temperatures, heavy elements like oxygen can absorb very specific wavelengths of high-energy X-ray light. The strategy was to use powerful X-ray telescopes to look at bright background sources and search for the telltale absorption signature of superheated oxygen. In 2018, and again in 2020, they found it. They detected the faint X-ray fingerprints of the WIM, confirming that a vast reservoir of hot, diffuse gas really does fill the cosmic filaments. The missing matter had been found, hiding in plain sight within the empty space. This wasn't just some leftover gas, it's the largest reservoir of normal matter in the nearby universe, a ghostly sea that outweighs all the stars in all the galaxies combined. But this cosmic ocean isn't just gas. It has castaways. There are lonely, rogue stars, adrift in the immense darkness of intergalactic space. These stellar outcasts were first confirmed in 1997 by the Hubble Space Telescope. While looking at the Virgo cluster of galaxies, astronomers found a huge population of stars that didn't belong to any single galaxy. They were just floating freely in between them all. And the number was staggering. The team estimated that these intergalactic stars could make up as much as 10% of the entire mass of the cluster. That's like a trillion suns wandering in the dark. So where did they come from? They are the refugees of cosmic violence. When galaxies collide and merge, the chaotic gravitational forces can act like a slingshot, flinging stars out of their homes and into the abyss. Another way it happens is when a binary star system gets too close to the supermassive black hole at its galaxy's center. The black hole's gravity can grab one star and violently eject its partner out of the galaxy at incredible speeds, sometimes over 2 million miles per hour. These are called hypervelocity stars. In 2012, a group of over 675 of these rogue stars were found at the edge of our own Milky Way, seemingly on a path straight for the Andromeda Galaxy. They were likely kicked out of our galactic center by our own supermassive black hole, Sagittarius A. It's thought that our black hole does this about once every 100,000 years. All these wandering stars together create a faint, diffuse glow called intracluster light. In some galaxy clusters, this ghostly light from countless homeless stars is actually brighter than the light from any single galaxy in the cluster. It's a haunting testament to the violent history of the cosmos, written not in the galaxies themselves, but in the lost souls scattered between them. The void, it turns out, is filled with the heat of the missing universe and the faint light of a trillion forgotten stars. The great cosmic recycling engine. We've found the universe's hidden skeleton and met its ghostly inhabitants. But this system isn't just a museum of cosmic leftovers, it's a dynamic and vital part of a grand cosmic ecosystem. It's a giant recycling engine. The gas in the intergalactic medium is on a constant journey.
Gravity pulls it along the cosmic filaments, funneling it like great rivers toward the galaxies. This inflow of pristine gas provides the raw fuel galaxies need to build new stars. Without this constant delivery, most galaxies would have run out of gas billions of years ago, and star formation would have just stopped. But it's not a one-way street. Once that gas gets into a galaxy and forms stars, it's change. Inside the fiery cores of massive stars, hydrogen and helium are fused into heavier elements like carbon, oxygen, and iron, the very elements that make up planets and life. When those massive stars die, they explode as supernovae. These explosions do two things. They seed the surrounding gas with these new heavy elements, and they create a powerful blast that drives huge amounts of this enriched gas out of the galaxy and back into the void. This process is called galactic feedback. It's how galaxies breathe. They inhale fuel from the cosmic web, and they exhale processed, enriched gas back out. This material then mixes with the gas in the filaments, enriching it with the heavy elements forged in the hearts of stars. And so the cycle begins again. This enriched gas now drifts through intergalactic space, sometimes for billions of years, until it's once again pulled by gravity back toward a galaxy to start the process over. This is cosmic recycling on the grandest scale imaginable. Matter isn't lost, it's just moved, transformed, and reused. Recent observations have given us direct proof of this incredible cycle. In 2023, astronomers used powerful telescopes to look at a massive galaxy 11 billion light-years away. They didn't just see gas falling into it, they detected the clear chemical signature of carbon in those inflowing streams. Carbon is an element that can only be made in stars. This was the smoking gun. It showed that the gas feeding this ancient galaxy wasn't just fresh material from the Big Bang. It was recycled gas that had already been through at least one generation of stars. This process moves an immense amount of material. The same cycle was seen in a galaxy named Mammoth 1, where recycled gas was flowing back in at a rate of about 700 times the mass of our Sun every single year. The universe isn't a collection of separate islands, it's a living system with a metabolism. The space between galaxies is its circulatory system, transporting the materials for life across cosmic distances. A universe reimagined. So, let's go back to where we started, that image of a bright galaxy in a silent, empty void. We can see it now with new eyes. The blackness isn't nothingness. It's a curtain drawn over a far more complex and interconnected reality. Behind that curtain is a universe woven together by a vast, invisible architecture, the cosmic web. The darkness isn't empty, it's filled with a ghostly sea of superheated gas, a cosmic wilderness populated by trillions of lost stars. And most importantly, this space is alive. It's the beating heart of a cosmic ecosystem, where matter is transported, transformed, and recycled in a perpetual cycle of birth, death, and rebirth. The very atoms that make you, forged in the heart of a long-dead star, may have spent a billion years drifting through this empty space before being gathered up to form our Sun and our Earth. In the most literal sense, we are creatures of the void. We are made of recycled stardust that once journeyed through the great, dark expanse between the galaxies. The discovery of this active, vibrant realm demolishes our old picture of the universe. There are no islands. There is only a single, unified cosmos, where the brightest galaxies and the darkest voids are all essential parts of the same grand, dynamic system. The next time you look up at the night sky, take a moment to appreciate the darkness in between the stars. Because it's in that darkness, in that perceived emptiness, that the deepest secrets, the grandest structures, and the very lifeblood of our universe are hidden. It's a reminder that even in a cosmos that seems so empty, everything is connected. And the greatest wonders are often found not in the light, but in the spaces between. Part 2. How far apart galaxies actually are. If you could somehow drift beyond the last bright stars of the Milky Way and turn around for one last look, our galaxy would not feel small. It would still look like a vast, luminous continent of light, stretching across a darkness so deep it would almost seem unreal. And yet, that would only be the beginning of the journey. Because the moment you leave one galaxy behind, you do not arrive anywhere new. You enter a silence so large that even the word distance starts to lose its meaning. This is where the real scale of the cosmos begins to reveal itself. We talk very casually about the space between galaxies, as if it were just another stretch of empty room, a gap, a crossing, a quiet space between one bright island and the next. But the truth is much stranger, and much harder for the human mind to hold on to. The distances between galaxies are not just big in the everyday sense. They are so vast that even our best analogies tend to collapse under the weight of them. And if this kind of slow journey through the universe helps you relax a little, you can gently like the video, subscribe, or leave a comment about where you're listening from tonight. It is always nice to imagine these thoughts drifting out into the night from all over the world. To really feel how far apart galaxies are, we have to begin somewhere smaller. Not small by human standards, of course. Space never truly gives us small, but small by cosmic standards. Let's begin with home. The Earth is about 93 million miles, or roughly 150 million kilometers, from the Sun. That already sounds enormous. It is such a large number that most of us stop emotionally processing it almost immediately. And yet, in cosmic terms, that distance is still local. It is so local that light from the Sun reaches us in about 8 minutes. Every sunrise is already slightly old by the time it touches your eyes, but only by a little. 8 minutes is still close enough to feel intimate. Now move outward to the edge of our solar system. Past Mars, beyond Jupiter, past Saturn and its pale rings, beyond Uranus and Neptune, out toward Pluto and the frozen debris beyond it. Even there, you are still at home. Even there, you are still inside a tiny neighborhood around a single star. Then comes the first true shock. The nearest star to our Sun, Proxima Centauri, is about 4.24 light-years away. A light-year is not a measure of time. It is a measure of distance. It is how far light can travel in 1 year, moving at nearly 300,000 kilometers per second, or about 186,000 miles per second. In a single second, light could circle the Earth more than 7 times. It is the fastest thing we know. And even for light, crossing the gap to the nearest star takes more than 4 years. Already, the universe is telling us something important. Space is mostly separation. Even inside a galaxy, the stars are not packed together the way they often look in pictures. From far away, the Milky Way seems like a smooth river of light. But that softness hides immense emptiness. The stars inside a galaxy are separated by distances so large that even our nearest stellar neighbor is unimaginably far away. And yet stars inside a galaxy still belong to the same city. That is the next step in understanding galactic distance. Before we talk about the space between galaxies, we need to understand the size of a galaxy itself. The Milky Way is a spiral galaxy a little over 100,000 light-years across, depending on where you choose to draw its faint outer edge. Our solar system sits far from the center, roughly 26,000 light-years out, orbiting in one of the galaxy's spiral regions. If you could travel at the speed of light, which we cannot, it would still take you around 100,000 years just to cross our galaxy from one side to the other. Pause on that for a moment. If all of recorded human history were compressed into a thin layer of dust, the time needed for light to cross the Milky Way would still tower above it. Agriculture, cities, empires, religions, modern science, every war, every invention, every language spoken by people still alive today, all of it would fit comfortably inside that crossing time. A beam of light could leave one end of the Milky Way before the first human city ever rose, and it still would not have made it all the way across by now. So a galaxy is not a small object. It is a continent of stars. A single large galaxy contains hundreds of billions of them, spread across an architecture of spirals, clouds, dust lanes, star nurseries, old clusters, dark matter, and long gravitational boundaries that reach even farther than the bright visible disk. And still, galaxies are separated from each other by distances much greater than their own size. That is where the mind begins to slip. The nearest large galaxy to the Milky Way is Andromeda. It is a spiral galaxy somewhat larger than our own, and it sits about 2.5 million light-years away. Not 2.5 light-years. Not 25. 2.5 million. If the Milky Way is about 100,000 light-years wide, then Andromeda is roughly 25 Milky Way widths away from us. Imagine standing on one island and looking toward another, only to learn that the water between them is not merely wide, but 25 times wider than the island you are standing on. That is the scale we are dealing with. Andromeda looks close in astronomical photos because the universe is often photographed without emotional scale. In the night sky, under dark conditions, it appears as a faint smudge, a soft oval, a whisper of light. It does not look impossible. It does not look unreachable. It just hangs there, quietly, like something distant but perhaps still approachable. But that smudge is a city of roughly a trillion stars, and the light entering your eyes left Andromeda about 2.5 million years ago. When that light began its journey, there were no human civilizations. There were no pyramids, no written languages, no telescopes, no maps, no music preserved on any instrument we would recognize. Even Homo sapiens had not yet appeared. The Earth was already old, but the human story had barely begun. The light simply traveled, year after year, through intergalactic darkness, until one clear night it reached your eyes and your brain quietly turned it into a faint patch of wonder. This is one of the strangest facts in astronomy. We do not see Andromeda as it is. We see it as it was in a deep prehistoric past. Now let's make the scale even more personal. Voyager 1, one of the fastest and farthest spacecraft humanity has ever sent into space, is moving at roughly 17 kilometers per second relative to the Sun. That is an astonishing speed by human standards. Fast enough to cross continents in minutes. Fast enough to escape the planets and leave the familiar heart of the solar system behind. And yet at that speed, reaching Andromeda would take tens of billions of years. Longer than the current age of the universe. Even if we imagine a spacecraft moving far faster than anything we have built so far, the problem barely softens. At 1% of the speed of light, which would be an almost miraculous engineering achievement by our current standards, reaching Andromeda would still take around 250,000 years. At 10% of light speed, it would still take about 25,000 years. Even light itself needs 2.5 million years. This is why the phrase, crossing the cosmic void, is so misleading in the best possible way. It makes the journey sound like a passage from one place to another. But in reality, the crossing is not really a trip in the ordinary sense. It is a surrender to time. To attempt it is to accept that the voyage itself may become larger than the civilizations that launched it. And Andromeda is only the nearest large galaxy. There are smaller dwarf galaxies closer to us, of course. The Magellanic Clouds orbit the Milky Way and are visible from the southern hemisphere. Other faint dwarf companions drift around us in the gravitational domain of what we call the local group. But if we are speaking about the next great spiral city in the dark, the next truly major galactic realm, it is Andromeda that waits in that impossible distance. The local group itself, the small family of galaxies to which we belong, stretches across several million light-years. It contains the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller dwarfs. Even this local neighborhood is vast beyond any ordinary intuition. It is less like a cluster of nearby houses and more like a network of lonely lanterns spread across a continent of darkness. And beyond the local group, the scale opens again. The Virgo cluster, the nearest large cluster of galaxies, lies roughly 50 to 60 million light-years away. That number becomes difficult to say with feeling, and that is part of the problem. The human brain did not evolve to grasp tens of millions of anything. We understand forests, rivers, mountains, storms, hunger, daylight, and shelter. We did not evolve to emotionally absorb a place so distant that its light began traveling toward us long before humans learned to make fire in the controlled way that shaped civilization. When astronomers map the universe, they do not find galaxies sprinkled evenly through the dark. They find vast structures, groups, clusters, filaments, walls, and between them, great regions of low density we call voids. So even when we say, the next galaxy, the reality is often more layered than that. There may be dwarf galaxies, stray stars, diffuse gas, hidden dark matter, and long filaments of invisible structure stretching through the black. But the key truth remains. The luminous islands we call galaxies are separated by distances so immense that the emptiness between them is one of the defining features of the universe. And this emptiness creates another beautiful consequence. Galaxies can collide without most of their stars actually hitting each other. That sounds absurd at first. If two great spiral galaxies merge, shouldn't their stars crash together in huge numbers? It seems obvious. But stars inside galaxies are so widely separated that even during a galactic collision, most of them simply pass by one another. The galaxy as a whole changes. The shape distorts. Gas clouds crash, star formation erupts, orbits shift, and gravity reshapes everything. But the individual stars mostly miss each other because the space between them is so vast. That fact alone tells you something profound about scale. If stars were packed more tightly, galaxy mergers would look like cosmic pileups. Instead, they are more like two enormous swarms of fireflies drifting through one another in slow motion, shaped by gravity over millions or billions of years. And our own Milky Way is expected to merge with Andromeda in roughly 4 to 5 billion years. This future collision is often described dramatically, but what makes it so haunting is the timescale. Right now, Andromeda is approaching us at a little over 100 kilometers per second. That sounds fast, and it is. But because the distance is so enormous, even at that speed the encounter takes billions of years to fully unfold. A galaxy can be moving toward you, and still remain unimaginably far away for longer than the lifespan of a star like our Sun has left to burn. So what does all of this really mean? It means the cosmos is not built like a crowded room. It is built like a vast and nearly unthinkable geography of isolation, connection, and patience. A galaxy is not just far from another galaxy. It is far in a way that changes the meaning of travel, of observation, of even the word nearby. When we say Andromeda is our nearest major galactic neighbor, that sounds comforting at first. Neighbor is such a domestic word. It suggests familiarity. A light across the street. A house beyond the fence. But in astronomy, neighbor can mean a place so far away that its light left before human beings existed in their present form. That is the scale we live inside. And there is something strangely calming about that, once the first shock fades. Because the distances between galaxies do not just tell us that the universe is large. They tell us that the universe is quiet, patient, spacious beyond urgency. Everything in daily life feels close and immediate. The mind is pulled toward deadlines, messages, anxieties, unfinished tasks, the weight of tomorrow. But above all of that, every clear night is a reality built on distances so large that even light must spend millions of years crossing them. The universe does not rush. A beam of light can leave a galaxy, travel for ages through darkness, and eventually arrive at another island of stars without ever encountering anything we would call familiar. A single photon can spend longer in transit between galaxies than our species has existed. And yet it arrives. Not quickly. Not dramatically. Just faithfully, crossing the void one immeasurably small step at a time. There is another subtle truth hidden inside these numbers. When you look at the night sky, you are not looking across empty space in the everyday sense. You are looking across time layered onto distance. The farther out you look, the older the light becomes. Nearby stars show you years-old light. Distant nebulae show you older scenes. And galaxies show you ancient histories. In that sense, the distance between galaxies is never just spatial. It is historical. To look far away is to look deep into the past. The cosmic void is not just a gap. It is an archive. And that changes how we should imagine a journey through it. Crossing the space between galaxies would not feel like sailing across a calm dark ocean toward a visible shore. There would be no nearby markers, no sense of ordinary progress, no growing coastline in the distance for most of the voyage. For a very long time, there would only be departure behind you and abstraction ahead. The destination would remain a faint ideal long after your home galaxy had fallen into the black. That, perhaps more than anything, is why these distances are so difficult to emotionally absorb. Our instincts are built for environments where movement leads to change we can feel. Walk far enough and the horizon shifts. Sail long enough and land appears. Travel long enough and a new country arrives. But intergalactic distance does not behave that way. It is too large to reward ordinary intuition. You can move very far by human standards and still be, cosmically speaking, nowhere. So when we ask how far apart galaxies actually are, the numbers matter. 100,000 light-years across for the Milky Way. About 2.5 million light-years to Andromeda. Tens of millions to nearby clusters. But the deeper answer is not just numeric. Galaxies are far apart enough that the darkness between them becomes a defining part of reality. Far apart enough that light itself turns into a slow traveler. Far apart enough that the idea of crossing from one to another stops sounding like exploration and starts sounding like a confrontation with time itself. And yet, for all that distance, these galaxies are still connected. By gravity. By ancient light. By dark matter. By the slow architecture of the cosmic web. They are not touching, but they are not meaningless to one another either. The void separates them, but it also gives shape to the universe they belong to. That is one of the most beautiful contradictions in astronomy. The cosmos is made of enormous separation, and yet nothing is entirely alone. If this gentle journey through the scale of the universe has settled something in your mind tonight, you can quietly leave a like, subscribe for more slow explorations, or share in the comments the moment when the numbers stopped feeling like numbers and started feeling real. Sometimes that happens with a single fact. Sometimes with a single image. For me, it is the thought of Andromeda's light leaving long before human civilization, and only now arriving here, soft and patient in the dark. Because once you truly feel how far apart galaxies are, the universe never looks the same again. The night sky stops being a ceiling of lights. It becomes a map of impossible distances, ancient messages, and vast silent roads between islands of fire. Part 3. Why empty space is not easy space. At first, it sounds almost comforting. If the space between galaxies is mostly empty, then perhaps crossing it should be simple. No traffic. No mountains. No weather. No crowded star systems to steer around. Just a long, silent stretch of darkness, waiting to be crossed. In the imagination, that kind of emptiness can feel gentle, peaceful, even. A smooth black sea with nothing in the way. But space has a strange habit of making simple ideas collapse. Because empty space is not the same thing as easy space. In fact, the very emptiness that makes intergalactic travel sound so clean and straightforward is exactly what makes it so brutally difficult. The problem is not only that the destination is far away. It is that almost everything we depend on to make travel possible disappears once the universe opens up around you. No air. No pressure. No warmth. No fuel stations. No natural shelter. No landmarks that mean anything on a human scale. No place to rest. No place to repair. No place to hide. And so tonight, as the darkness stretches farther outward, the real challenge begins to come into focus. Not just how far the galaxies are from one another, but why the emptiness between them is one of the harshest environments the universe can offer. Because once you leave the crowded brightness of stars behind, you do not enter a simple road. You enter a place where almost every natural condition works against life, against machines, and against the ordinary idea of a journey. If these quiet explorations help you settle in for the night, you can gently like the channel, subscribe, or leave a comment about what part of the universe feels most calming to you. It is always nice to imagine these slow thoughts traveling through the dark from one quiet room to another. To understand why empty space is so hard, it helps to begin with something very human. Here on Earth, when we travel, we rarely think much about the environment itself. We complain about traffic, weather, delays, or rough roads, but the world is still built to support us. The air is already there. Gravity holds us to the ground. Water exists in rivers, oceans, and clouds. Temperatures shift, but usually within ranges our bodies and machines can endure. Even in remote places, the Earth still surrounds us with matter, with atmosphere, with friction, with signs that we are somewhere. Travel on Earth happens inside a system that sustains life by default. Space offers the exact opposite. The moment you leave Earth, you leave the environment your body was built for. And the farther you go, the more complete that abandonment becomes. Intergalactic space is not just a larger version of a desert or an ocean. It is a place where the basic assumptions of life stop being true. There is no breathable air because there is effectively no air at all. There is no pressure pressing gently against your skin. There is no medium to carry sound. There is no shared temperature in the ordinary sense. There is no sky. There is no horizon. There is no up or down. There is only vacuum, radiation, scattered particles, weak traces of gas, and distance so large that the idea of location starts to thin out. Even the word empty can be misleading. Intergalactic space is incredibly sparse, but it is not magically harmless. A vacuum is not a soft thing. It is not gentle. It is a condition of absence, and living things do not handle absence very well. Human beings are not merely organisms that like oxygen and water. We are pressure-dependent systems. The fluids in our bodies, the exchange of gases in our lungs, the stability of our tissues, all of it depends on being embedded inside an environment with the right balance of conditions. Remove those conditions, and survival becomes a constant act of technological resistance. A spacecraft, then, is not really a vehicle in the normal sense. It is a tiny moving bubble of stolen Earth. That is what makes the emptiness so difficult. The ship must bring almost everything with it. Air must be carried or endlessly recycled. Water must be recovered, purified, and reused. Waste must be managed. Heat must be controlled. Every system that Earth provides freely must be recreated artificially inside a fragile shell moving through the most indifferent environment imaginable. And once the journey stretches beyond planets, beyond nearby stars, and into the gulf between galaxies, that problem stops being temporary. It becomes the whole story. One of the great illusions created by science fiction is that space travel is mainly about engines. Build a powerful enough ship, point it outward, and the problem is solved. But propulsion is only one part of the challenge, and not always the most unforgiving one. The deeper issue is sustainability. How do you keep a machine alive, and perhaps a crew alive, in a place where nothing around you wants to help? On Earth, machines break all the time, and we barely notice the miracle of how repairable life is here. Parts can be replaced. Fuel can be delivered. Tools can be shared. Expertise can be reached. Even in isolated places, there is still a planet under you. But a spacecraft in deep space has no such safety net. Every component must keep working. Every backup must function. Every tiny flaw becomes more serious because there is nowhere natural to stop and fix it. This is one reason empty space is so deceptive. It looks obstacle-free, but that lack of obstacles also means a lack of support. In a mountain range, the terrain is dangerous, but it is still terrain. In the middle of an ocean, conditions are severe, but there is still water beneath you, air above you, and a planet holding everything together. In intergalactic space, there is no surrounding system that cares whether you continue to exist. There is another problem, one that sounds almost philosophical at first, but becomes very practical the longer you think about it. In ordinary travel, movement can be measured by what changes around you. A road curves. A coastline grows nearer. A city appears on the horizon. The landscape reassures you that progress is happening. Human beings are deeply comforted by visible change. We like movement that can be felt and confirmed. But in truly empty space, especially on an intergalactic scale, almost nothing changes in a humanly satisfying way. For a very long time, the stars behind you would still look like stars. The destination ahead would still be faint, abstract, and impossibly far away. Even if you were moving at an unimaginable speed, the voyage might not reward you with the emotional experience of getting closer. That may sound like a minor psychological issue, but on long journeys it becomes profound. A trip without meaningful environmental change is not just physically difficult, it is mentally strange. It strips away one of the oldest comforts travel has ever offered, the feeling that the world itself is acknowledging your movement. And then there is the issue of energy. On Earth, energy is everywhere around us in useful forms. Chemical energy in fuels, electrical energy through power grids, solar energy above us every day, hydroelectric power, batteries, engines, and layered infrastructure. A traveler rarely carries everything they will ever need from beginning to end. They move through a world that can resupply them. In deep space, the farther you go from stars, the less useful the surrounding environment becomes. Near Earth, sunlight is abundant enough to power spacecraft with solar panels. Move farther out, and sunlight fades quickly. By the time you reach the outer solar system, solar power is already far weaker. In the space between galaxies, far from bright stars, the background light of the universe still exists, but it is thin, cold, and not remotely practical in the way we would need. A ship must bring energy with it, generate energy from carried fuel, or rely on power sources so durable and compact that they border on the miraculous by current human standards. And every power source introduces more demands. Fuel has mass. Mass is hard to accelerate. More mass requires more energy. More energy systems require more maintenance, more shielding, more cooling, more redundancy. The ship becomes a moving argument against simplicity. That is another reason emptiness is not ease. When the environment gives you nothing, you must carry your answer to everything. Even temperature, which sounds simple from the safety of a blanket or a quiet room, becomes a strange problem in space. People often imagine space as uniformly freezing, and in a broad sense it is extremely cold. The average background temperature of the universe is only a few degrees above absolute zero. But a spacecraft does not simply become cold and stay cold in a neat way. Thermal control in vacuum is difficult because heat cannot leave by ordinary air contact, since there is no air. It must be radiated away. Meanwhile, onboard systems generate heat. Electronics produce heat. Human bodies produce heat. Power systems produce heat. In sunlight, surfaces can become intensely hot. In shadow, they can become bitterly cold. So the ship is caught in a constant balancing act, trying to preserve an interior climate suitable for life and machinery while drifting through a place that offers no stable external comfort at all. And unlike on Earth, where a change in temperature can often be survived by clothing, shelter, or a fire, in space temperature control is built into the survival of the vehicle itself. If the ship cannot manage heat, it cannot manage life. Then comes the question of motion. In everyday life, stopping feels easy. We are so used to friction that we barely think about it. Take your foot off the pedal, and the car slows down. Drop a ball, and gravity guides it to rest. The world constantly helps motion come to an end. Space does not. In vacuum, an object in motion tends to keep moving. That sounds elegant in a physics classroom, and it is. But for travel, it means every meaningful change in speed costs energy. To accelerate, you need propulsion. To slow down, you also need propulsion, unless you can use the gravity or atmosphere of some massive body to help you. But intergalactic space offers very little to work with. There are no planets waiting to assist. No thick atmospheres for braking. No convenient orbital mechanics near most of the route. A ship crossing the cosmic void must not only gain speed, it must also eventually lose it. And both of those actions carry enormous energetic consequences. It is one thing to imagine launching yourself into emptiness. It is another thing to imagine arriving anywhere in a controlled way. And there is a more subtle difficulty hidden here. In a place with almost no friction and almost no external references, navigation becomes a delicate art. You would rely on instruments, stars, distant signals, and precise calculations. But over immense spans of time, tiny errors matter. A very small deviation in angle can grow into an enormous miss across millions of light years. The emptiness offers little forgiveness. If you are wrong by a little, you may end up wrong by a galaxy. This is where deep space becomes less like sailing and more like threading a needle in the dark while the needle and the thread are both moving. Another problem with empty space is that it is poor in resources, but not perfectly clean. That combination is particularly cruel. If space were full of helpful material, a ship might someday learn to harvest what it needs. If it were truly nothing at all, at least the hazards would be easier to predict. But the real universe gives you traces. Thin gas, dust, high-energy particles, radiation fields. Not enough to support you, yet enough to threaten you. A single grain of dust sounds harmless until velocity enters the story. At very high speeds, even tiny particles can carry tremendous energy when they strike a spacecraft. What feels like emptiness on a human scale can still hide impacts that matter. This is not the kind of danger that appears as dramatic explosions every few minutes. It is more patient than that, more statistical, more indifferent. But on long journeys, patient dangers are often the ones that win. Radiation is another quiet enemy. Space is filled with energetic particles from stars, supernovae, black holes, and other violent processes scattered across the cosmos. Earth protects us from much of this with its magnetic field and atmosphere. Strip those away, and the body becomes more exposed. So do electronics. Long-term radiation can damage living tissue, increase cancer risk, degrade materials, and interfere with the very systems keeping the journey alive. In intergalactic space, away from many local sources of interference, some backgrounds may be cleaner in specific ways, but the general truth remains. Empty space is not a sheltered place. It is an open one. And openness, in the universe, is rarely kindness. Perhaps the hardest part to emotionally grasp is that emptiness removes not only physical support, but temporal support. On Earth, time is structured by cycles: sunrise and sunset, weather, seasons, meals, sleep, noise in the distance, other people moving through the day. The world constantly reminds us that time is passing and that we belong to it. In deep space, especially on a journey lasting years, centuries, or far more, those natural rhythms must be invented artificially. Light cycles must be created. Living spaces must be designed. Psychological structure must be maintained against monotony so complete that it becomes almost geological. Human beings can endure many hardships when there is change around them, when there is contact, when there is a sense of narrative. But empty space offers very little narrative unless the travelers create it themselves. That makes the voyage not only an engineering problem, but a psychological one. How do you remain human in a place that offers none of the ordinary mirrors of human life? No weather, no landscapes, no biological world, no spontaneous sound, no smell of rain, no rustling trees, no distant traffic, no changing sky. Just the interior of the ship, the hum of systems, and beyond the hull a darkness so complete that it no longer feels like night. It feels like separation itself. This is one reason long-duration space travel often leads scientists to talk less like physicists and more like caretakers. They speak about habitat design, circadian rhythms, social stability, cognitive load, emotional resilience. Because once you leave a living world behind, survival is not only a matter of preventing death. It is also a matter of preserving meaning, preserving sanity, preserving the sense that the journey still belongs to beings like us. There is also the uncomfortable truth that machines age. On Earth, technology feels replaceable because our civilization is full of backups. But a ship crossing deep space cannot casually swap out a failing system. Materials fatigue. Radiation accumulates damage. Microscopic impacts add up. Lubricants degrade. Seals weaken. Electronics suffer. Any mission lasting extremely long durations would have to solve a problem humanity has never truly solved at scale: how to create a self-sustaining technical world that can outlast generations without depending on a planet-sized industrial base behind it. It is one thing to build a powerful machine. It is another thing to build a machine that can remain trustworthy when the nearest help is not just far away, but effectively unreachable. And this brings us to one of the strangest ideas of all. Sometimes, emptiness is harder precisely because it offers so little resistance. That sounds backward, but think of how many earthly systems rely on interaction with their environment. Wings need air. Boats need water. Brakes rely on friction. Sound needs a medium. Even heat exchange often depends on contact. Much of engineering, in its deepest form, is a negotiation with the surrounding world. But in vacuum, many of those ordinary negotiations vanish. The ship is forced to become more self-contained, more internally complete, more dependent on what it already carries and what it can already do. It becomes less like a traveler and more like a sealed ecosystem. So when people imagine the space between galaxies as an open road, the truth is almost the opposite. Roads are useful because they are embedded in a world. They connect places full of fuel, shelter, repair, signs, and life. The cosmic void is not a road. It is the absence of road. It is what remains when almost every convenience of travel has been removed and only distance is left behind. And yet there is something strangely beautiful in that severity. Because the emptiness between galaxies reveals a deeper truth about the universe. The stars are not floating in a friendly medium. Life is not surrounded by natural hospitality. The cosmos, on its largest scales, is sparse, cold, and indifferent. And the fact that life exists at all within such a universe makes life feel even more delicate, more improbable, and in its own quiet way, more precious. We are creatures of a warm shoreline, born on the edge of a small star, wrapped in atmosphere, protected by magnetism, sustained by liquid water and inherited rhythms. To imagine crossing the cosmic void is to imagine carrying that entire inheritance into a place that did not prepare itself for us. That is why empty space is not easy space. Because difficulty is not always created by obstacles. Sometimes it is created by the absence of everything that would have helped you. Sometimes the hardest environment is not the one filled with violence, but the one filled with almost nothing. A place so empty that survival becomes an act of constant invention. A place so silent that every working system inside a ship becomes a tiny rebellion against the conditions outside it. If this part of the journey has made the universe feel a little wider tonight, you can quietly subscribe, leave a like, or share a thought in the comments. Maybe the idea that stays with you is not the distance itself, but the strange fact that emptiness can be one of the harshest things in existence. Because that is the lesson the void keeps teaching us. The darkness between galaxies is not simply blank. It is demanding. It is costly. It is patient. It asks a terrible price from anything that tries to cross it. Not because something is there to stop you, but because almost nothing is there to help you. And once you truly understand that, the silence of intergalactic space begins to feel different. Not peaceful in the ordinary sense. Not cruel in any personal sense. Just vast, clean, and utterly uninterested in whether a traveler makes it through. Which, somehow, makes the fragile warmth of home feel brighter than ever. Part 4. The speed problem. Why, very fast, is still too slow. There is a quiet trick the universe plays on us whenever we think about travel. On Earth, speed feels like the answer to distance. If something is far away, we move faster. If the road is long, we take a plane instead of a car. If a message must cross the world, we send it at the speed of light through cables, satellites, and screens. In ordinary life, speed solves problems. Faster usually means better. Faster means closer. Faster means possible. And because that logic works so well here, it is natural to carry it with us into space. If the gap between galaxies is enormous, then perhaps the solution is simple. Build something unimaginably fast. Faster than any rocket. Faster than any probe. Faster than anything humanity has ever made. Push hard enough, long enough, cleverly enough, and eventually even the cosmic void begins to shrink. But this is where the universe becomes strangely humbling. Because in the space between galaxies, very fast stops meaning what we think it means. Speeds that would look miraculous by human standards barely register against cosmic distance. Speeds that would transform our civilization still leave us crawling through the dark. And even the fastest thing we know, light itself, is forced to spend millions of years crossing the gap from one great galaxy to another. Tonight, the question is no longer just how far galaxies are apart, or how empty the void is. Now we arrive at the next hard truth. Even if you could move incredibly fast, the universe is so large that speed alone may never feel like enough. Because the problem is not only motion, it is scale, it is time, it is the uncomfortable fact that the cosmos is large enough to make even brilliance feel slow. And if these calm journeys through space help you settle into the night, you can softly like the channel, subscribe, or leave a comment about which part of the universe feels most impossible to picture. I always like imagining these thoughts drifting quietly from one listener to another across the world. To begin understanding the speed problem, we need to return to something simple. Human beings are not good at feeling large numbers. We can read them, compare them, even work with them mathematically. But emotionally, our minds prefer scales that fit inside ordinary experience. A minute, an hour, a day's drive, a mountain, a coastline, a city. Once numbers become too large, they stop behaving like reality in our imagination. They become labels. And that is exactly what happens when we talk about space. Take a car moving at highway speed. It feels fast. The world slides past. Distance begins to collapse. A city that once seemed far away can be reached by afternoon. Step up to an airplane, and the effect becomes even more dramatic. Countries fold toward one another. Oceans shrink into overnight routes. Human civilization has been shaped by this feeling that motion can conquer scale. Then consider Earth's orbit around the Sun. Our planet moves at roughly 30 kilometers per second, or about 67,000 miles per hour. That is far faster than any jet, and yet we do not feel it because everything around us is moving together. Earth itself is already racing through space with astonishing speed. The solar system adds more motion on top of that. The Sun orbits the center of the Milky Way at roughly 220 kilometers per second. Again, astonishing. Again, silent. Again, not enough to make the galaxy feel small. This is the first great shift in perspective. The universe is not waiting still while we decide how to move through it. Everything is already in motion. Stars orbit galaxies. Galaxies drift within clusters. Clusters move within larger structures. And against that grand moving background, our usual sense of speed begins to look almost provincial. Now let us think about the fastest thing we know. Light travels at about 300,000 kilometers per second. It can circle the Earth more than 7 times in 1 second. It can travel from the Moon to Earth in a little over a second. It reaches the Sun from Earth in about 8 minutes. By all human standards, light is unimaginably fast. It is not just fast. It feels absolute. Final. Nothing outruns it. Nothing catches it. It is the speed limit written into the fabric of reality. And yet even light struggles with the scale of the cosmos. Light from the Sun takes 8 minutes to reach Earth. That sounds manageable. Light from Neptune takes hours. Light from the nearest star beyond our Sun, Proxima Centauri, takes more than 4 years. Already, even at the fastest speed in the universe, the distance to the nearest star begins to feel serious. Now cross the Milky Way. Light needs around 100,000 years. Then go farther, to Andromeda, the nearest major galaxy. Light needs about 2.5 million years. That number deserves to be felt slowly. A beam of light leaving Andromeda begins its journey when no human city exists, when writing does not yet exist, when agriculture has not yet reshaped the human world. It travels through darkness for 2.5 million years, never slowing, never resting, never stopping, and only then does it arrive here as a faint smudge in the night sky. That is not a problem of engineering. That is a problem of cosmic scale. And once you understand that, the speed problem begins to look much more severe. If even light requires millions of years to cross intergalactic space, what hope is there for anything slower? Let's bring this down from abstraction to something humanity has actually built. Voyager 1 is one of the fastest and most distant spacecraft ever launched by our species. It is moving at roughly 17 kilometers per second relative to the Sun. That is astonishingly fast for an artifact built by human hands. It has traveled farther than any other spacecraft, entered interstellar space, and become one of the great technical achievements in our history. But against the gap between galaxies, Voyager is almost still. At its current speed, reaching the nearest star system would take tens of thousands of years. Reaching Andromeda would take tens of billions of years, longer than the current age of the universe. That is one of the most quietly devastating facts in astronomy. A machine that represents some of the finest ambition our species has ever launched into space would not make it to the nearest major galaxy before the universe itself becomes older than it is now by a staggering margin. So perhaps, you think, Voyager is simply too primitive. Fair enough. Let us imagine something much faster. Suppose humanity someday builds a spacecraft that can reach 1% of the speed of light. That would be 3,000 kilometers per second. Not slightly better. Not incrementally better. It would be a revolutionary leap beyond any propulsion system we currently possess. At 1% of light speed, reaching Proxima Centauri would still take more than 400 years. Reaching Andromeda would take about 250,000 years. 250,000 years. That is still not a voyage in the ordinary sense. It is an era. It is a span of time so large that human history, from the earliest tools to the modern world, would occupy only a portion of it. Civilizations would rise, disappear, be forgotten, and turn to dust during the trip. So let us be even more generous. Suppose we reach 10% of the speed of light, which is a truly extraordinary thought. At that speed, Proxima Centauri could be reached in a few decades. Suddenly, interstellar travel begins to look emotionally possible, at least in theory. But Andromeda would still take around 25,000 years. Even after making one of the greatest engineering leaps imaginable, even after building a vessel so advanced it would make modern spacecraft look ancient, the nearest major galaxy is still not a destination for a human lifetime. It is barely a destination for a civilization. This is the heart of the speed problem. Cosmic distances grow faster than intuition. Each improvement in speed feels dramatic to us, but the universe absorbs it almost without reaction. And there is another layer to this. When we say a spacecraft is moving at 1% or 10% of light speed, we often imagine that speed as if it came freely. As if the ship simply reaches that velocity and then the problem becomes mostly solved. But speed is not free. Every gain in velocity demands energy, and the faster you want to go, the more difficult the build becomes. This is where physics begins to tighten the rules. To accelerate an object, you must give it energy. The more mass it has, the more energy it needs. A tiny probe is one thing. A crude spacecraft with life support, shielding, supplies, redundancy, and long-duration systems is something else entirely. And as speed rises, the energy required rises dramatically. Not only must you accelerate the ship, but if you ever want to arrive somewhere in one piece, you must also slow it down again. Acceleration costs energy. Deceleration costs energy. Carrying the fuel to do both makes the ship heavier, which then demands more energy still. The problem turns back on itself like a spiral. This is one reason interstellar travel already looks difficult. Intergalactic travel pushes that difficulty into another category entirely. There is also the uncomfortable truth that extremely high speed makes the environment more dangerous. In ordinary life, speed mainly changes travel time. In deep space, speed also changes the violence of impact. A grain of dust hitting a spacecraft at enormous velocity is no longer a tiny inconvenience. It becomes a serious event. At a substantial fraction of light speed, even very small particles can strike with terrifying energy. So the faster you move, the more protective engineering you may need, which adds mass, which adds energy demands, which loops the problem again. The universe does not merely ask how fast you want to go. It asks what you are willing to pay for that speed. And there is one more subtle problem with speed, one that often disappears inside popular imagination. Fast travel sounds impressive because we usually think in terms of top speed. But the lived reality of a journey also includes the long time spent getting up to that speed and coming back down from it. If a spacecraft accelerates too hard, its crew might not survive. Human bodies are not indifferent to force. Even with gentler acceleration, reaching substantial fractions of light speed could take long periods. And then, long before arrival, deceleration must begin. So the elegant fantasy of a ship racing through the void at magnificent speed hides a more complex truth. Much of the journey may involve careful, extended changes in velocity rather than a single glorious burst forward. And all the while, the clock continues. This brings us to a fascinating twist in the story, because once velocities become high enough, time itself begins to behave differently. Einstein's theory of relativity tells us that time is not universal in the way common sense suggests. If you move fast enough relative to someone else, time for you can pass more slowly than it does for them. This is called time dilation, and it is one of the strangest, most beautiful features of modern physics. It has been tested in experiments. Clocks moving at different speeds really do disagree, by tiny but measurable amounts. At everyday velocities, this effect is negligible. But at speeds close to the speed of light, it becomes profound. Imagine a spacecraft traveling at a very high fraction of light speed. From the perspective of people on Earth, the trip might take thousands or millions of years. But for those on board, less time might pass. In that sense, relativity offers a strange kind of mercy. It does not make the distance smaller in the ordinary sense, but it changes the traveler's experience of the journey. This is where many minds feel a moment of hope. Perhaps, after all, sufficiently high speed can save us. Perhaps if time slows enough on board, then even the gulf between galaxies becomes personally manageable. But here again, the universe keeps its dignity. To get time dilation strong enough to seriously shorten a trip to another galaxy, you would need to travel astonishingly close to the speed of light. Not 10%, not 20, much closer. The engineering demands become almost beyond language. The energy required becomes extraordinary. The hazards grow. The challenge of shielding, navigation, acceleration, deceleration, and long-term system survival intensifies. Relativity is real, yes, and beautiful, yes, but it is not a magical loophole handed to us for free. It is another layer of physics that both helps and complicates the problem. And even if the travelers could personally experience a shorter trip, the outside universe would continue aging without them. The ship might arrive in a future far beyond the civilization that launched it. Home could become memory, legend, or complete disappearance. So even time itself cannot fully rescue the old dream of speed as a simple answer. There is something quietly haunting about this. We are a species that learned to cross rivers, then seas, then oceans, then skies. At each stage, speed expanded our world. Faster ships connected continents. Faster planes connected civilizations. Better communication made the planet feel small. It is deeply tempting to believe that space is simply the next version of that same story, waiting for a more advanced engine. But intergalactic space may not belong to that narrative. It may be something else. A scale so vast that even triumph remains slow. A realm where the distance is not merely hard, but fundamentally transformative. Where travel stops being an extension of transportation and becomes a challenge to time, biology, engineering, and continuity itself. Perhaps the best way to feel this is to imagine a destination that moves the moment you try to reach it. Galaxies are not fixed decorations on a static background. The universe is expanding. On the largest scales, distant galaxies are being carried away from one another as space itself stretches. For nearby galaxies like Andromeda, gravity still dominates the local relationship, and Andromeda is actually approaching us. But for more distant targets, the expansion of the universe becomes part of the problem. The farther out you aim, the more the fabric of space joins the conversation. So speed is not only fighting distance. Sometimes it is also fighting a changing cosmic stage. And this helps explain why astronomers speak so often in the language of light and time. Not because they are trying to be poetic, though the subject often is, but because ordinary distance units stop being useful when the universe grows this large. Kilometers and miles become too small too quickly. Even the light year, once you think about it carefully, is a confession of scale. It tells you that the best unit we can comfortably use is the distance traveled by the fastest thing in the universe over the course of an entire year. And still, galaxies are millions of those units apart. That is why, very fast is still too slow. Because our instincts for speed were shaped in a world where distances are modest and environments are forgiving. In the cosmic void, speed remains powerful, but it no longer feels sovereign. It no longer guarantees that a destination becomes practical. It only changes the flavor of the impossible. There is a humbling comfort in that. The universe is not mocking us. It is simply large on terms we did not evolve to understand. It lets light move at its absolute limit, and even then it asks for patience measured in ages. It does not bend itself around our preferences for convenience. It does not turn the space between galaxies into a route just because we would like one. And yet perhaps that is part of what makes the cosmos so soothing to contemplate at night. It is honest in its vastness. It asks nothing of us but perspective. It reminds us that scale can be beautiful even when it refuses to be useful. If you have ever looked at a distant galaxy in a photograph and felt, for a moment, that it seemed reachable, that is understandable. The eyes are kind. They compress distance into images the mind can carry. But the physics behind the picture is far colder and far grander. That soft spiral glow may be a city of stars millions of light years away, and the light touching your eyes tonight began its journey before our species had a name for itself. Once you absorb that, speed starts to feel different. Not useless. Never useless. Speed still matters. It shapes what stars we might someday reach, what probes we might send, what futures open or close before us. But on intergalactic scales, speed stops being a triumphant solution and becomes a measure of humility. A reminder that no matter how fast we dream, the universe can still remain patient. If this quiet descent into cosmic scale has brought a little calm to your night, you can gently like the channel, subscribe, or leave a comment with the moment that made the size of the universe feel real to you. For some people, it is the thought that light takes years to reach the nearest star. For others, it is the thought that even light takes millions of years to cross to Andromeda. For me, it is this: that somewhere right now, in the darkness between galaxies, countless photons are still traveling. Not rushing, not hurrying, just crossing the void with perfect, tireless obedience to the laws of nature. They are moving as fast as anything can move, and even they are still not there yet. And somehow that makes the universe feel both larger and quieter than before. Part 5: The Energy Problem, What It Takes to Keep Moving. There is a quiet moment hidden inside every dream of space travel. It comes after the excitement of launch, after the engines ignite, after the ship rises beyond the atmosphere, after the familiar world falls away beneath it. In imagination, that is often the moment when the hard part feels complete. The vehicle is finally moving. Space is open. The destination is somewhere ahead in the dark. And from there, it is tempting to picture the rest as a kind of glide. A long, silent passage through emptiness, carried forward by momentum and hope. But the universe is rarely that generous. Because movement is not free. Not on Earth, not in orbit, and certainly not in the vast emptiness between galaxies. To keep moving across truly cosmic distances, a spacecraft does not simply need courage, or cleverness, or a good map. It needs energy. A staggering amount of it. Energy to accelerate. Energy to power life support. Energy to keep computers running, systems stable, temperatures controlled, communications alive. Energy to correct mistakes. Energy to survive. And if the destination is not just a nearby world but another galaxy entirely, then the question of energy stops being a technical detail and becomes one of the deepest obstacles in the entire journey. Tonight, the problem becomes more concrete. Not just how far the crossing is, or how empty the void feels, but what it actually costs to keep a ship alive and moving when the road is millions of light years long. Because the farther you go into the dark, the less the universe gives you for free. And the less it gives you, the more you must carry, create, conserve, and protect on your own. If these slow journeys through the universe help you settle your thoughts at night, you can gently subscribe, leave a like, or share in the comments which part of space feels most difficult to imagine. It is always a strangely comforting thought that people all over the world are lying awake, or drifting towards sleep, wondering about the same distant things. To understand the energy problem, it helps to begin with something simple and familiar. On Earth, most movement feels easy because the world hides the real cost from us. You get into a car and drive for hours without thinking too much about what is actually happening. Fuel is refined elsewhere, transported elsewhere, stored nearby, and delivered through a system so vast and dependable that it begins to feel invisible. Electricity comes through wires. Batteries are charged by networks we did not build ourselves. Heating and cooling happen at the touch of a button. Even when something is expensive, it is still embedded inside a civilization designed to make energy available. Travel here works because the planet is already doing much of the work for us. Roads exist. Air exists. Gravity behaves in familiar ways. Fuel can be found. Repairs can be made. If one engine fails, help is not millions of miles away. Our machines move inside a giant support system, and because that system is so normal to us, we often forget it is there. Space removes that comfort almost immediately. A spacecraft cannot pull over. It cannot stop at a station. It cannot casually tap into some cosmic grid waiting in the dark. Whatever energy it needs, it must either bring with it, generate from systems it carries, or gather from an environment that is often too sparse to help in any practical way. This is difficult even inside our own solar system. Stretch that problem across the gulf between galaxies, and it becomes almost overwhelming. The first part of the challenge is the most obvious one. Acceleration takes energy. If you want to move a spacecraft faster, you need to push it. That sounds simple, but physics quickly turns the simplicity into something heavier. The more mass the spacecraft has, the harder it is to accelerate. And a serious interstellar or intergalactic craft would have a great deal of mass. Structure, shielding, engines, fuel, backup systems, thermal control, communication arrays, guidance systems, maybe scientific payloads, perhaps even a habitat for life if people were somehow on board. Every useful thing adds weight. Every kilogram becomes part of the burden the engines must fight against. That means the energy problem begins before the ship has even truly left home. To move something through space, A spacecraft usually throws mass in the opposite direction. Hot gas, ionized particles, perhaps something more exotic in future concepts, but the principle is often the same. You push matter one way so the ship goes the other. That means propulsion is not only about energy in the abstract. It is about fuel, reaction mass, efficiency, and the uncomfortable fact that the fuel you carry makes the ship heavier, which means you need more energy to push the fuel that is meant to help you move. This creates one of the oldest frustrations in rocketry. To carry more fuel, you need a bigger ship. But a bigger ship requires more fuel. And more fuel adds more mass, which demands more fuel still. It is a loop that engineers have wrestled with for generations, and it is one reason rockets look the way they do, massive stacks of propellant carrying comparatively tiny payloads. Now imagine scaling that problem far beyond the Moon, beyond Mars, beyond the outer planets, beyond the nearest stars, and into the intergalactic dark. Even saying it softly makes the difficulty feel heavier. Because if a ship is trying to cross the cosmic void, it does not just need enough energy to become fast. It may need enough energy to remain functional for durations that feel almost geological. And that changes the nature of the mission. The energy system is no longer simply the thing that starts the journey. It becomes the heart of the entire civilization inside the ship, whether that civilization is a handful of systems or a habitat full of minds. There is also a second problem, quieter but just as serious. Keeping something moving is not the same as keeping something alive. A stone thrown into empty space will keep traveling for a very long time. It does not need air. It does not need food. It does not need heat regulation, medical systems, navigation updates, or radiation shielding. It is not trying to stay conscious. It is not trying to preserve electronics over centuries. It is not trying to maintain a breathable atmosphere inside a metal shell. A spacecraft, by contrast, is not just an object in motion. It is a fragile pocket of order resisting failure every second. And resisting failure takes power. Lights, computers, pumps, environmental controls, communications, sensors, internal circulation, water recycling, air processing, waste management, navigation instruments, redundancy systems. Even a relatively small modern spacecraft depends on a web of interlocking components. In the short term, this is manageable. Over days, months, even years, we can design machines to endure remarkable missions. But once the journey begins to stretch towards centuries, then millennia, then longer still, every watt becomes part of a much larger question. How do you build a power system that can remain dependable not just for a mission, but for an age? Near Earth, solar energy can do a surprising amount of work. Sunlight is abundant here. Solar panels quietly power satellites, probes, stations, and instruments. Even far from Earth, solar systems can still be useful, though their output falls rapidly with distance. By the time you move deep into the outer solar system, sunlight is already weak enough that missions often need other sources, such as radioisotope power systems, because the sun no longer provides enough energy per square meter to be practical for everything. And this is still inside one star system. In the vast spaces between galaxies, sunlight in the ordinary sense becomes less and less helpful. A ship drifting far from stars would still be surrounded by radiation of various kinds, by the faint glow of the universe, by diffuse light from distant galaxies, but not in a form generous enough to power a demanding spacecraft the way sunlight supports a satellite near Earth. The background cosmos glows, yes, but it does not nourish in the way a nearby star does. This means a deep space vessel may need to become, in effect, its own star in miniature. Not in brightness, but in function. It must carry within itself the source of the energy that keeps everything going. And that leads us into one of the strangest realities of long-distance space travel. The ship is no longer just transportation. It becomes an energy economy. Every system begins to matter in terms of consumption and survival. How much power does guidance need? How much do communication systems need if they must send signals over impossible distances? How much energy is lost to heat? How efficiently can waste be recycled? How much redundancy can be afforded? At what point does comfort become a liability? At what point does simplicity become necessity? If human beings were ever inside such a vessel, the problem would deepen even more. People do not simply exist on low power. We need air, water, stable temperatures, nutrition, medical care, psychological structure, and protection from the hostile environment outside. Even in the most minimal scenario, a human habitat would multiply the energy burden far beyond what a simple robotic probe might require. And yet robotic missions have their own burdens too. Machines can survive cold better than people. They do not need oxygen. They do not get lonely in the human sense. But they still depend on power. Sensors, processors, communications, orientation systems, protective mechanisms, data storage, autonomy routines. The longer a mission lasts, the more the design must anticipate not just ordinary consumption but degradation, failure, and the possibility that one system may need to compensate for another. In a way, all-along missions become lessons in scarcity. On Earth, scarcity is often local. A battery runs low, so you recharge it. Fuel runs low, so you refill. A city needs more electricity, so it draws from a wider network. In the void between galaxies, scarcity is total. There is no wider network. There is only what the craft has, what it can make, and how carefully it can survive on both. This is why energy in space is not just a problem of quantity. It is a problem of quality and endurance. A giant burst of power is impressive, but it is not enough. A truly cosmic journey requires power that is stable, efficient, durable, and intelligently managed over spans of time that stretch beyond normal engineering culture. A power source that lasts 10 years is admirable. A power source that lasts 100 years begins to feel extraordinary. A power source that remains trustworthy over thousands of years almost sounds mythic. And still, even that might not be enough for a crossing between galaxies. There is another cost hidden inside the dream of speed. The faster you want to go, the more punishing the energy demands become. This is where the human imagination often cheats a little, because it likes clean stories. Build a more advanced engine. Find a clever new fuel. Harness fusion. Use antimatter. Invent a breakthrough. And yes, future physics and engineering may one day allow propulsion systems far beyond what we have now. But even generous imagination does not erase the scale of the challenge. Powerful engines still need power sources. Exotic systems still have to obey conservation laws, thermal limits, storage problems, safety risks, and the brutal arithmetic of mass and velocity. At high enough speeds, the spacecraft is not merely moving. It is carrying enormous kinetic energy, and that energy had to come from somewhere. And if the goal is not just to pass through a distant region but to arrive in a controlled way, then another painful fact appears. Stopping also takes energy. This is one of the places where ordinary intuition fails us. On Earth, we are surrounded by friction. Motion naturally bleeds away. Air slows us. Road contact slows us. Gravity helps shape trajectories into rest. But in deep space, especially far from planets or stars that might help with gravitational maneuvers, slowing down is your own responsibility. A ship racing through the dark must eventually shed its speed if it wants to enter orbit, approach safely, or do anything more graceful than simply rush past its destination. So a serious journey needs power not just for departure, but for arrival. The trip is not half the problem. It is the whole curve of motion, from start to cruise to finish. And there is something almost cruel in the way this compounds. To carry the fuel needed to stop, you make the ship heavier, which means you need more energy to accelerate it in the first place. It is as though the future burden of arrival reaches backward and makes departure harder too. Some proposed ideas try to escape this trap. light sails pushed by lasers, ramjets that might collect sparse particles from space, fusion systems, antimatter concepts, beamed power, staged missions, self-repairing probes. None are foolish ideas. In fact, many are beautiful ideas. But each one moves the difficulty rather than erasing it. The universe always seems to ask the same quiet question in return. Where will the energy come from, and how will you carry the cost? There is also the matter of heat, which often receives less attention than it deserves. When machines use energy, some of it becomes useful work, and some of it becomes waste heat. On Earth, excess heat can often be dispersed through air, water, or contact with the surroundings. In vacuum, that process is much trickier. A spacecraft must radiate heat away. That takes design, surface area, materials, and careful balancing. Too much heat, and systems fail. Too little heat in the wrong place, and systems fail differently. A ship trying to survive deep time in deep space must not only generate energy, but handle the thermal consequences of using it. So even success creates new burdens. Power the craft more strongly, and you may create more heat than you can easily shed. Reduce power use too much, and essential systems may become fragile. The ship becomes a constant negotiation between enough and too much. In long, quiet journeys, efficiency becomes almost a moral principle. Waste is no longer bad merely because it is inefficient. It is bad because it threatens survival. A sloppy design that might be tolerated in a short mission becomes dangerous in a long one. Every unnecessary watt becomes a small leak in the future. Every overbuilt system may burden the propulsion problem. Every underbuilt system risks collapse years or centuries later. This is one reason truly long-range space travel tends to push thinking toward closed loops. Recycling, reuse, regeneration. Systems that do not consume resources carelessly, because carelessness only makes sense when there is a world nearby to forgive it. And intergalactic space forgives almost nothing. There is, however, a deeper layer to the energy problem, one that is not merely engineering but existential. Energy is what allows order to resist the natural slide toward disorder. A living habitat, a working computer, a pressurized cabin, a stable temperature, a functioning communication array, all of these are forms of maintained order. They do not happen automatically. They are held in place by continuous effort. The moment that effort stops, systems begin to fail, temperatures drift, structures weaken, chemistry changes, life support loops collapse. So when we ask what it takes to keep moving across the cosmic void, we are really asking what it takes to keep order alive in a place where disorder waits patiently outside every wall. That is what makes the ship feel less like a vehicle and more like a candle carried through a stormless but indifferent night. Not because the darkness is attacking it, but because the darkness offers no support at all. The flame continues only as long as the system that protects it continues. And perhaps that is why the idea of energy in space feels so profound. On Earth, we experience energy mostly as convenience. In deep space, energy becomes something closer to permission. Permission for air to circulate. Permission for water to remain useful. Permission for thought to continue inside warm rooms that should not exist in the cold. Permission for memory, navigation, observation, and hope. Take enough energy away, and the voyage ends long before the destination. This is why some scientists and engineers quietly favor robotic futures over human ones for the deepest missions. A machine can be leaner, simpler, less demanding. It can power down for long periods. It can tolerate certain extremes more easily. It can be built around narrower goals. If the universe is going to charge a terrible price for energy, perhaps a small and patient traveler stands a better chance than a large and delicate one. And yet, even then, the energy problem remains. A robotic mission to another galaxy would still require propulsion beyond anything humanity has ever achieved, durability beyond anything we have yet mastered, and power systems designed for timescales that make ordinary projects feel brief and fragile. The machine might not need to breathe, but it would still need a future. There is something calming in all of this, strangely enough, because the energy problem reminds us that the universe is not crossed by will alone, not by intelligence alone, not by imagination alone. All of those matter, beautifully. But the cosmos also demands substance, fuel, power, endurance, real physical cost. The universe is not a place where grand ideas float freely into reality. It is a place where every motion leaves an accounting. And maybe that is part of what makes it so worthy of wonder. A galaxy is not far away in some poetic sense only. It is far away in the hard language of joules, mass, thermodynamics, and time. The void is not merely dark. It is expensive. Every dream of crossing it must eventually stand before the same patient truth. Moving through reality costs something. If this part of the journey has settled gently into your thoughts tonight, you can quietly like the channel, subscribe for more slow explorations, or leave a comment about the idea that stayed with you most. Sometimes it is the distance. Sometimes it is the silence. And sometimes it is this, the realization that even motion itself must be paid for. Because in the end, the energy problem is not really about engines. It is about what it takes to sustain intention across impossible distance. A spacecraft leaving one galaxy for another would not just be carrying metal, fuel, and instruments. It would be carrying a long refusal to stop. A decision made against the ease of drifting, against the weakness of systems, against the entropy of time. Every watt used inside that ship would be part of the same quiet declaration. Keep going. Keep the lights on. Keep the air moving. Keep the memory of home alive a little longer. And the darker the space around it becomes, the more extraordinary that small persistence begins to seem. Part 6: Radiation, Dust, and the Hidden Dangers of Intergalactic Space. If you were asked to imagine the most dangerous place in the universe, you might picture something dramatic. A black hole tearing light apart. A star exploding in a violent flash. A planet with crushing gravity or oceans of fire. Our minds are naturally drawn to danger that looks dangerous. The kind that announces itself. The kind that roars. But the universe often does something quieter than that. Sometimes, the worst danger is not something large enough to see coming. It is something patient. Something thinly spread. Something almost invisible. A place that looks calm from a distance, but slowly wears down anything that tries to cross it. And that is part of what makes the space between galaxies so unsettling. From far away, intergalactic space seems clean, empty, peaceful, even. Just darkness stretching from one island of stars to another. But the silence hides its own kind of threat. Not because the void is crowded with monsters, but because it contains just enough danger to matter, and just little enough comfort to offer no protection from it. Tonight, the journey moves deeper into that darkness. Because once you understand the distance, and once you understand how hard it is simply to keep moving, the next question becomes even more personal. What is actually out there? What would a ship be exposed to during a journey that lasts not days or years, but perhaps centuries, millennia, or more? What would slowly strike it, seep into it, damage it, age it, and test it? And the answer is not one thing. It is a whole quiet collection of things. Radiation, dust, stray particles, invisible gas, high-energy fragments from ancient cosmic violence, the hidden weather of a place that most people still call empty. If these quiet explorations help you unwind at night, you can gently like the channel, subscribe, or leave a comment about which part of space feels the most mysterious to you. It is always comforting to think of these thoughts drifting softly through the night, from one quiet room to another. To begin, it helps to notice something about the word empty. When we say a room is empty, we do not mean it contains literally nothing. It may still have air, dust, temperature, faint sounds, the smell of wood or fabric, the soft movement of light. Empty usually means empty enough for our purposes. Empty enough to feel vacant. The same is true of space, but on a far stranger scale. Intergalactic space is unbelievably sparse. The number of particles out there can be incredibly low compared to anything we experience on Earth. In some regions, you may find only a few atoms in a volume that, by earthly standards, would seem absurdly large. By normal intuition, that feels like nothing. But when a journey is long enough, and when a spacecraft is vulnerable enough, even almost nothing becomes something. A single atom is tiny. A single speck of dust is tiny. A single burst of radiation may pass unnoticed. But crossing the cosmic void would not be about 1 second, 1 hour, or one pass-through danger. It would be about enduring exposure over unimaginable spans of time. And over long enough durations, the universe does not need to hit hard. It only needs to keep hitting. That is one of the deepest truths of space travel. In the void, danger is often cumulative. Perhaps the most famous of these hidden threats is radiation. Radiation is one of those words people hear often, but rarely feel clearly. It can sound abstract, almost too scientific to picture. But in simple terms, radiation is energy moving through space, sometimes in the form of waves, sometimes in the form of fast-moving particles. Some radiation is ordinary and harmless in the amounts we encounter. Sunlight is radiation. Warmth from a fire is radiation. Radio waves are radiation. But some forms are far more energetic, and far more capable of damaging living tissue and machines. Out in space, especially far from the protection of a planet like Earth, radiation becomes a constant presence. Here on Earth, we are sheltered in ways we rarely stop to appreciate. Our atmosphere absorbs and scatters many dangerous forms of incoming radiation. Our magnetic field helps deflect large numbers of charged particles from the sun and from deeper space. The planet itself is a kind of protective cradle, wrapped around us so completely that we can forget how exposed the wider universe really is. A ship in intergalactic space would have no such cradle. It would be open to the wider radiation environment of the cosmos. That includes high-energy particles known as cosmic rays, along with other energetic emissions from sources scattered across the universe. Some come from the sun and other stars. Some come from supernovae, the explosive deaths of massive stars. Some may come from black holes, active galactic nuclei, and other violent corners of the cosmos. Some have traveled for astonishing distances, carrying with them the memory of ancient events. What makes this especially unsettling is that radiation does not need to look dramatic to be dangerous. There may be no visible flash, no great warning, no obvious sound, because sound does not travel through vacuum. A cosmic ray can simply pass through shielding, through circuits, through the body itself, leaving behind tiny tracks of damage. A single event may do little, or it may do a lot, depending on energy, angle, materials, bad luck. But over time, the exposures build. For human beings, this matters deeply. Living tissue is delicate. Cells are constantly dividing, repairing, communicating, maintaining the long, fragile balance we call life. High-energy radiation can break chemical bonds, damage DNA, increase cancer risk, injure organs, alter the nervous system, and create health problems that unfold slowly rather than all at once. It is not like being struck by a visible weapon. It is more like a patient erosion, taking place at the smallest levels of the body. And in deep space, far from hospitals, far from gravity, far from the protective systems of Earth, even ordinary medical care would already be difficult. Add chronic radiation exposure, and the human problem becomes heavier still. Machines suffer too, though in different ways. Spacecraft electronics are remarkably advanced, but they are not invincible. High-energy particles can disrupt memory, flip bits in computer systems, degrade sensors, weaken materials, and slowly age the very circuitry a mission depends on. Radiation does not have to destroy a spacecraft in one spectacular moment. It can simply make it less trustworthy, less precise, less stable, less able to survive the long future it was built for. That is one of the reasons long-duration missions are so difficult to imagine clearly. We tend to think in terms of launch and arrival, but the real struggle may lie in the long middle, in the silent years when systems must continue working while invisible damage accumulates. And radiation is only one part of the story. There is also dust. Now, dust sounds almost harmless. On Earth, dust is something we wipe from a shelf. Something that gathers quietly in corners. Something soft enough to ignore until sunlight reveals it hanging in the air. It does not sound like a cosmic threat. But speed changes everything. A tiny grain of dust moving slowly is not much. A tiny grain of dust striking a spacecraft at enormous velocity is something else entirely. Energy depends not just on mass, but on motion. Even very small particles can hit with serious force when relative speeds become extreme. This is true inside our own solar system, where spacecraft must already account for micrometeoroids and fine debris. But in the broader spaces between stars and galaxies, the problem takes on a different character. There may be far fewer particles, but over very long journeys, and at high speeds, even rare collisions matter. It is another example of the cruel logic of the void. There is not enough material out there to help you, but there is enough to hurt you. A spacecraft crossing intergalactic space might encounter atoms, dust grains, thin gas clouds, and stray particles too sparse to notice moment by moment, yet persistent enough to become a design problem over centuries or longer. At truly high speeds, even hitting diffuse hydrogen becomes significant. A sparse medium that sounds almost imaginary in everyday language becomes more real when the ship is tearing through it fast enough for every encounter to count. And because these dangers are so small, shielding becomes difficult in its own way. How do you protect a ship from things that are nearly invisible, widely scattered, and relentless over huge spans of time? You add material, layers, Whipple shields, magnetic ideas, clever engineering, redundancy. You build sacrificial surfaces meant to absorb impacts before they reach something more important. You protect critical electronics. You place habitats deeper inside the structure. You choose materials carefully. You anticipate damage and design around it. But every layer of protection adds mass. And mass, as we have already seen, makes the energy problem worse. This is one of the most frustrating patterns in deep space travel. Every solution comes with a price. Shield the craft more heavily, and it becomes harder to accelerate. Make it lighter, and it becomes more vulnerable. Build for longevity, and the ship grows more complex. Build for simplicity, and perhaps it becomes more fragile. The universe never gives the easy version of the problem. There is also the strange matter of gas. We often talk about intergalactic space as though it were pure vacuum, but in truth there is a thin intergalactic medium, a faint spread of particles and gas stretched across enormous distances. In some regions, especially around clusters and filaments, this medium can become hotter, denser, and more active than people might expect. Not dense in any ordinary human sense, of course. Nothing like atmosphere. Nothing like clouds over a city or mist over water. But real enough to shape galaxies, carry heat, respond to gravity, and influence what crosses it. Some of this gas is extremely hot, heated by shock waves, gravitational collapse, galactic activity, and the long unfolding structure of the cosmic web. It does not glow in a way the human eye could appreciate from nearby, but instruments can detect its presence. This means that the void between galaxies is not just blank darkness. It is laced with faint structure, and some of that structure is hostile. A ship moving through such regions would not feel weather in the earthly sense. No wind against the hull. No clouds gathering. No rain. But on long timescales, the environment would still matter. Particles impact surfaces. Heat and radiation fields vary. Plasma and magnetic influences may become relevant. The voyage would move through a hidden ecology of low-density danger. And that hidden ecology has another effect. It makes navigation and prediction harder. When danger is large and visible, you can see it. You can steer around it, at least in principle. But when the hazard is thin, diffuse, and statistical, the problem becomes less like dodging a mountain and more like preparing for years of bad weather that may never fully declare itself. The ship must be ready not only for known threats, but for the long possibility of unknown cumulative ones. This is one reason intergalactic travel remains so much harder to imagine than simple science fiction sometimes suggests. In fiction, danger often comes as an event: a meteor storm, a radiation burst, a dramatic systems failure, something sharp enough to frame a chapter around. The real universe may be less theatrical, and therefore more difficult. The true danger may be years of exposure, tiny strikes, slow degradation, aging materials, compounding failures, a navigation system that becomes slightly less reliable, a sensor that loses precision, a shield that carries the record of 10,000 unnoticed impacts, a crew exposed not to one great catastrophe, but to 1,000 quiet assaults too small to make a story out of until, eventually, they do. That kind of danger is harder to emotionally grasp because it does not behave like myth. It behaves like time. And time, in the cosmic void, is always one of the hidden enemies. Even something as simple as a surface on the outside of a spacecraft becomes part of this long argument with the universe. Materials expand and contract with changing thermal conditions. They are struck by particles, bathed in radiation, slowly altered by chemistry and physics in a place where no repair shop waits nearby. Protective coatings degrade. Microscopic cracks may grow. Components become older not just in years, but in exposure. A mission lasting a few months can survive a great deal through careful design. A mission lasting decades is already a remarkable technical achievement. But a mission lasting centuries or beyond begins to feel less like an engineering project and more like a wager against the long patience of reality. There is also something haunting about the psychological side of hidden danger. Visible danger at least gives the mind something clear to respond to. You see the storm. You hear the warning. You feel the urgency. The body knows how to mobilize around a threat that has edges. But what happens when the danger is everywhere and nowhere? When it is built into the background? When the voyage itself is a long exposure to things that cannot be watched directly and may not reveal themselves until much later? For a human crew, that kind of uncertainty could become exhausting. Every system check might carry a small shadow behind it. Every strange reading might raise the question of what invisible process has been quietly unfolding. Every year of apparent calm might still be another year of particles crossing walls and leaving tiny signatures inside metal, memory, and bone. And yet this is not a reason to panic. In a strange way, it is a reason to respect the subtlety of the cosmos. Because the universe is not only dangerous in its obvious violence. It is dangerous in the way deep winters are dangerous, in the way deserts are dangerous, in the way oceans are dangerous when they seem calm. Not because they are malicious, but because they are not built around human survival. They do not hate us. They simply do not rearrange themselves for our comfort. Intergalactic space follows the same principle. It is not trying to destroy a traveler. It is simply full of conditions that make survival difficult. Open radiation fields, sparse but meaningful matter, energetic particles, thin gas, long durations, isolation. The traveler brings vulnerability into a place that did not prepare for it. That is why the phrase hidden dangers feels right. The threats are not hidden because they are mysterious in some magical sense. They are hidden because the human eye is not made to see them, and the human nervous system is not made to intuit them. A galaxy looks bright. A nebula looks dramatic. A black hole sounds terrifying. But radiation, dust, and thin gas do not offer themselves to the imagination so easily. They are quiet. They do not glow with theatrical warning. They simply wait inside the background. There is one more layer to this that feels especially beautiful, even as it is sobering. The same universe that threatens a traveler with radiation and dust is also the universe that records its own history in those very things. Cosmic rays tell stories of violent origins. Dust is the residue of stars, the ash of ancient processes, the fine debris of creation and destruction. Intergalactic gas traces the web-like structure of the cosmos, linking galaxies through a hidden architecture. In other words, the things that endanger a journey are often the same things that reveal what the universe is made of. Danger and knowledge come from the same darkness. A traveler crossing the void would not merely be passing through empty space. They would be moving through the leftover signatures of cosmic history, through particles born in explosions long finished, through dust forged in the lives and deaths of stars, through the thin breath of the cosmic web itself. And perhaps that is part of what makes the idea so mesmerizing. The void is not dead. It is not blank. It is active in its own faint way, scarred by old violence, structured by gravity, filled with traces, alive not like a forest or a sea, but alive with process, with consequence, with invisible motion. And anything that tries to cross it must accept that it is entering not a blank corridor, but a subtle and ancient environment. If this part of the journey has made the universe feel a little deeper tonight, you can quietly leave a like, subscribe for more slow explorations, or share in the comments which hidden danger surprises you most. For many people, it is radiation. For others, it is the thought that even dust can become deadly when velocity turns small things violent. For me, it may be this: that the greatest dangers in the cosmic void are not the ones that scream. They are the ones that whisper, the ones that drift, the ones that pass through, the ones that gather their effect over years too long to hold comfortably in the mind, the ones that remind us that the universe does not need claws or fire to be formidable. Sometimes it only needs distance, exposure, and time. And once you begin to understand that, intergalactic space stops feeling merely empty. It starts to feel weathered, filled with faint, relentless pressures. A place where even silence is not truly harmless. A place where every successful crossing would require not just speed and power, but endurance against things almost too small to see. And that makes the warmth of a protected world, with its atmosphere and its magnetic field and its soft ordinary shelter, feel more miraculous than ever. Part 7, The Human Problem. Can any crew survive the journey? There is a moment in almost every dream of deep space travel when the ship feels real. The engines are there. The hull is there. The destination has a name. The darkness ahead is immense, but somehow manageable, because imagination has already done what it always does. It has turned the impossible into a picture. A vessel moving quietly through the stars. A crew inside it. A window, perhaps. A long mission, yes, but still a mission. Still something a human story could hold. And then a softer, more difficult question arrives. Not whether a ship could make the journey, at least in theory. Not whether the physics can be imagined, or the energy can be calculated, or the route can be traced across a map of distant light, but whether human beings could actually endure it. Whether flesh and memory and emotion and aging and loneliness could survive inside that metal shell long enough to matter. Whether a human life, so brief and so delicate, could remain human at all while crossing a distance measured not in days or years, but in centuries, millennia, or far more. Because the deeper problem of intergalactic travel is not only about space. It is about us. It is about the kind of creatures we are. Warm-blooded, social, fragile, dependent on gravity, light, food, sleep, rhythm, touch, care, and continuity. Creatures shaped by a living planet and by an evolutionary story that took place under a sky, inside weather, among other living things. We are not built for the void. We are built for shorelines, forests, rivers, families, seasons, dawn, hunger, shelter, and the quiet repeated signals that tell the body it belongs somewhere. So tonight, the journey becomes more intimate. Because once the distances become real, and once the hidden dangers of the void begin to settle into view, the next question is no longer just whether the ship survives. It is whether the people inside it still can. And if these slow journeys into science and space help you settle in at night, you can quietly like the channel, subscribe, or leave a comment about what part of the universe feels most human to you. Sometimes it is strange how a vast and indifferent cosmos can still make us feel closer to our own lives. To understand the human problem, it helps to begin with something we often forget. Human beings are local creatures. That sounds obvious, but it matters more than it first appears. Every system inside your body assumes an Earth-like world in the background. Your bones assume gravity. Your muscles assume resistance. Your lungs assume pressure. Your eyes assume cycles of light and dark. Your brain assumes regular signals from the environment, other people, familiar sounds, changing spaces, shared routines, and the countless subtle cues that make ordinary life feel stable. Even here on Earth, when those conditions shift too much, the body notices. Spend a long time isolated, and the mind changes. Stay in darkness too long, and sleep changes. Remain inactive too long, and the body weakens. Lose a sense of purpose, and even time itself begins to feel heavy and uncertain. This is true in quiet offices, in remote outposts, on long hospital stays, in polar stations, on submarines, and in lonely apartments. Human beings do not need a dramatic crisis to begin unraveling. Sometimes all it takes is enough separation from the things that quietly keep us regulated. Now extend that separation into deep space. Not for a week, not for a season, not even for a few years, though even that would be a profound challenge. Extend it for spans so long that the voyage itself begins to outgrow the natural structure of a human life. That is where the human problem becomes almost unbearable to think about clearly. The first and most obvious issue is lifespan. A person is not a spacecraft. A machine can, at least in principle, be designed for endurance beyond any single generation. A human being cannot. Even under ideal conditions, the human body ages. Cells accumulate damage. Organs slowly change. Systems lose resilience. Memory shifts. Strength declines. That is simply part of being alive. So if the nearest major galaxy is millions of light years away, and even extraordinary speeds still imply journey times far beyond any normal lifespan, then a conventional crewed mission stops making sense almost immediately. A crew can survive hardship. A crew cannot survive 25,000 years. This is one of those facts that seems almost too simple, and yet it quietly destroys a great deal of romantic imagination. You can picture brave astronauts setting out toward another galaxy. You can hear the music, see the stars, imagine the courage. But the math remains untouched by all of it. Human beings do not live long enough. So perhaps the answer is not one crew, but many. This is where the idea of a generation ship begins to appear. A vessel so large, so self-contained, and so durable that the people who launch it would never be the people who arrive. Children would be born on board, then grandchildren, then generations after them. The ship would become less like a vehicle and more like a moving world, carrying a society rather than a crew. It is a powerful idea, also a deeply unsettling one. Because the moment a mission outlasts the people who chose it, something changes. The voyage is no longer just exploration. It becomes inheritance, obligation, a social system designed to continue itself long after the original decision-makers are gone. And that raises questions that are not only biological or engineering related, but moral and psychological. What does it mean to be born into a journey you did not choose? What does destination mean to a child whose whole world is the inside of a ship? What happens when home is not a planet behind you or a world ahead of you, but simply the machinery that contains your life? These are not technical problems in the usual sense, but they may matter just as much as fuel or shielding. Human beings do not live by oxygen alone. We live by narrative, by identity, by belonging, by the sense that our effort is connected to something meaningful and shared. A generation ship might solve the lifespan problem in one sense, but it creates an entirely new challenge in another. How do you preserve purpose over centuries? How do you stop the mission from becoming a myth, then a burden, then a forgotten ritual? Because over long enough spans of time, memory changes, cultures change, language shifts, priorities drift, records are lost, stories simplify themselves. Conflicts emerge, new values appear. A ship that begins as a project of science may, generations later, feel more like a sealed civilization trying to maintain stability inside a machine it only partially understands. That thought is both fascinating and quietly terrifying. And even if the social problem could somehow be solved, the body remains. One of the strangest things about human beings is how dependent we are on forces we never notice. Gravity is a perfect example. On Earth, it is so constant and so ordinary that it disappears into the background of daily life. You stand, walk, lift, stretch, sleep, and live inside gravity without thanking it for a second. But take gravity away, and the body begins to protest. We already know from space missions that the human body changes significantly in microgravity. Muscles weaken because they no longer fight weight in the usual way. Bones lose density because they are not stressed as they are on Earth. Fluids shift through the body in unusual patterns. Balance changes. Vision can be affected. The heart and circulatory system adapt to a very different environment. Even after relatively short periods in orbit, astronauts must work hard to maintain health and to readjust when they return. Now imagine that not for months, but for years. Then imagine it not as a temporary mission, but as the permanent condition of life. A crew crossing intergalactic space could not simply trust that the body would remain itself. The ship might need artificial gravity, whether through rotation or some other future method, simply to keep the passengers human in the long term. Without something like that, the voyage could become an experiment in gradual biological transformation, not into anything better, but into something less adapted, less resilient, less able to return to any planetary world at all. And then there is sleep. Sleep sounds gentle compared to engines and radiation, but sleep is one of the hidden foundations of mental stability. Humans are rhythmic creatures. Our bodies are tuned to cycles of light and dark, activity and rest, day and night. Even in ordinary life, when those rhythms are badly disturbed, the mind begins to blur at the edges. Concentration falters. Emotions become harder to regulate. Memory suffers. Anxiety rises. The sense of time distorts. On a long deep space mission, there is no natural dawn. No sunset drifting through trees. No weathered sky changing color. No season quietly altering the feel of the day. Every rhythm would need to be designed. Light cycles, work cycles, shared meals, quiet hours, artificial morning, artificial evening. The ship would need to create not only air and water, but also time as the body understands it. That may sound small, but it is not small at all. Because one of the easiest ways to lose yourself is to lose the rhythm that tells your nervous system where you are inside the day. On Earth, time comes to us from outside. In space, time must be built indoors. The psychological side of this becomes even heavier when you consider isolation. Human beings are profoundly social, even when we imagine ourselves as independent. We regulate one another. We borrow calm from other people. We borrow structure from community. Even strangers in a city, even distant lives glimpsed through windows, even the hum of ordinary civilization, help reassure the mind that it belongs to a wider world. A deep space crew would live with extreme social limitation. the same faces, the same voices, the same walls, the same routines. No new weather. No ordinary privacy in the full earthly sense. No spontaneous encounters. No walking away into a wider world when tension builds. On long enough timescales, even a well-chosen crew could begin to feel the weight of emotional repetition. This is why psychologists who study isolation often care less about dramatic breakdowns and more about subtle erosion, small misunderstandings, quiet resentments, uneven workloads, loneliness that becomes difficult to name because there is no clear event causing it. The soft narrowing of experience until life begins to feel compressed. The mind does not always fail in spectacular ways. Sometimes it simply becomes tired of being enclosed. And enclosure would define such a mission. The ship might be large by spacecraft standards, but tiny by human standards. A few rooms, corridors, compartments, systems behind panels, artificial gardens, perhaps, if the mission were advanced enough. Shared spaces carefully designed to feel less mechanical than they truly are. Yet beyond all that effort would still remain the central fact. Outside the walls is not landscape, not sky, not open air, only vacuum and distance. For some people, that thought is peaceful. For others, it is unbearable. And in truth, both reactions might live side by side inside the same person. There is also the problem of meaning over time. A short mission can borrow its purpose from urgency. A crew can endure hardship when there is a clear destination, a clear window of effort, a clear sense that suffering will end and achievement will follow. Human beings are often strongest when sacrifice feels bounded. But what happens when the mission lasts longer than anyone's life? What happens when arrival becomes something you believe in but will never personally see? That kind of distance changes the emotional structure of purpose. Some people might still find it noble, a service to the future, a continuation of a larger human story. But others might begin to feel the burden differently. Why endure all this for a world you will never touch? Why maintain a system whose reward belongs to descendants you will never meet? Why preserve a destination that may, over generations, stop feeling real? Again, this is not just philosophy. It is mission stability. A long journey cannot survive on machinery alone. It must also survive on belief. And belief is fragile. Then comes medicine. Even on Earth, with hospitals, specialists, imaging systems, laboratories, supply chains, and centuries of accumulated knowledge available almost instantly, the human body remains difficult to maintain. Illness happens. Injury happens. Emergencies happen. New diseases appear. Chronic conditions develop. Pregnancy, aging, mental health crises, unexpected complications. All of it belongs to the ordinary reality of life. In a sealed ship crossing the cosmic void, medicine becomes radically more difficult. You cannot call for evacuation. You cannot transfer a patient to a better facility. You cannot rely on resupply from a nearby world. The craft must carry not just tools, but deep medical capability, perhaps even the means to manufacture equipment, synthesize drugs, perform surgery, manage long-term care, and adapt to problems the designers never predicted. And that means the mission must not only transport human life, it must sustain an entire moving culture of care. A human crew also brings reproduction into the story, whether anyone wants that complication or not. On a journey lasting beyond one lifetime, future generations become part of the equation. But reproduction in an artificial environment raises enormous unknowns. How does long-term low gravity or artificial gravity affect pregnancy and development? How do radiation exposure, closed habitats, nutrition limits, and psychological stress shape the health of children born during the journey? How do you maintain genetic diversity across generations? How do you build a society stable enough for children to grow into adults without the wider support structures of a planetary civilization? These are not small questions. They are civilization-level questions folded into a vehicle. And beneath all of them remains the simplest truth of all. Human beings need more than survival. We need beauty, too, though we do not always call it that. We need variety. We need some sense of wider life. A tree outside a window. Rain against a roof. The smell of soil. A path that leads somewhere. Birds. Streets. The casual freedom to move through space that is not entirely planned. The body and mind draw nourishment from the ordinary richness of a living world, even when we are too busy to notice it. A ship can preserve function. Can it preserve enough humanity to make survival feel like life? That may be the most difficult question in the whole journey. Because a crew that is technically alive but emotionally diminished, culturally brittle, physically degraded, and psychologically exhausted is not truly flourishing. It is enduring. And endurance, while noble, is not the same thing as a livable future. This is why some thinkers are drawn instead to suspended animation, cryogenic sleep, or other ideas that try to reduce the burden of long human duration. If people could somehow sleep through most of the voyage, perhaps lifespan and psychological strain could be softened. It is an alluring thought. Close your eyes in one era, open them in another. But even that carries its own uncertainties. Human biology is not a machine that can simply be paused and restarted without consequence. We do not yet know how to preserve a person safely across such timescales, or whether the body and brain would tolerate it at all. And even if it were possible, the ship would still need to continue functioning perfectly in the meantime. The burden would shift, not disappear. There is a quiet irony in all of this. We often imagine deep space travel as the ultimate expression of human strength, our boldest act, our farthest reach, our most glorious proof that intelligence can outgrow its birthplace. And perhaps, in some future age, it may be. But the closer you look, the more another truth begins to emerge. The greatest challenge may not be crossing the void. It may be carrying humanity through it without losing what humanity is. Our bodies were shaped by Earth. Our minds were shaped by company, weather, mortality, and place. Even our sense of hope is often rooted in short horizons we can emotionally hold. Next season. Next year. A child growing older. A journey that ends within a life. Intergalactic travel asks us to imagine something much harder. A mission that outlasts not only bodies, but cultures, meanings, and generations. And in that sense, the human problem is not an obstacle on the side of the mission. It is the mission. Can a crew survive the journey? Perhaps, if survive means only that biological life continues inside a functioning ship for long enough. But if survive means remaining fully human, physically healthy, psychologically stable, socially coherent, morally intact, and meaningfully connected to the purpose of the voyage, then the question becomes much more difficult. Maybe impossibly difficult. At least for now. And yet there is something beautiful in asking it. Because the question reveals how extraordinary ordinary life already is. Gravity holding your body in place. Fresh air entering your lungs. Day becoming night without anyone programming it. A meal shared in a kitchen. A walk outside without a helmet. The presence of trees, dogs, traffic, clouds, strangers, insects, and all the soft living signals that tell the nervous system it belongs to a world. These things can feel small until you imagine losing them for good. If this quiet part of the journey has made home feel a little more precious tonight, you can gently like the channel, subscribe for more slow explorations, or leave a comment with the part of ordinary Earth life you think a deep space crew would miss most. For some, it would be rain. For others, open skies. For others, simply the freedom to step outside. For me, it may be this. That on Earth, life is never fully alone. Even in silence, there is wind. Even at night, there are living things nearby. Even in difficult times, the planet still surrounds you with a kind of background companionship. Air, gravity, horizon, seasons. the quiet ongoing presence of a world that knows how to hold life. And perhaps that is why the idea of a human crew crossing the cosmic void feels so moving. Not because it proves we are made for such journeys, but because it reminds us, gently and honestly, how much of being human depends on the fragile miracle of already being home. Part 8. Could robots, AI, or generation ships do better? By now, the human problem has become hard to ignore. The distances are too large. The voyage is too long. The body is too delicate. The mind is too dependent on rhythm, place, and familiar life. Even if a ship could be imagined, and even if the energy could somehow be found, the question keeps returning in the same quiet form. Could people really be the right travelers for a journey like this? It is one of the most intimate and humbling questions in all of space exploration. Because for so much of human history, travel has meant presence. If we wanted to understand a mountain, we climbed it. If we wanted to cross an ocean, we boarded the ship ourselves. If we wanted to set foot on the moon, it was not enough to send machines alone. We wanted eyes there, hands there, breath there. Human beings have always carried a deep instinct to make discovery personal. But the universe does not always reward that instinct. Sometimes the scale becomes so large, and the cost becomes so severe, that another possibility begins to seem more realistic. Perhaps the best traveler is not the most courageous one, nor the strongest one, nor even the most intelligent in the human sense. Perhaps the best traveler is the one most suited to patience, the one least troubled by isolation, by repetition, by silence, by time itself. And that is where robots, artificial intelligence, and generation ships enter the story. Not as perfect answers. The universe rarely offers those, but as different kinds of answers. Different ways of imagining what a crossing might look like if it were shaped not around the limits of one human lifespan, but around endurance, continuity, and systems that can remain meaningful even when the journey becomes too long for ordinary life to hold. Tonight, the question is no longer whether the cosmic void is hard to cross. We already know that it is. The question is whether some other kind of traveler might stand a better chance than we do. Whether a machine can outlast flesh. Whether intelligence can continue without a living crew awake inside the ship. Whether a civilization in miniature could be carried through the dark from one age to another. And if these slow journeys into deep space help ease your mind at night, you can quietly like the channel, subscribe, or leave a comment about which future feels most believable to you. A robotic mission, an AI-guided ark, or a ship carrying generations through the dark. It is always interesting to imagine how different people picture the long future of travel. The simplest alternative to a human crew is also, in many ways, the most practical. Robots. A machine does not need oxygen. It does not need a warm meal, a sunrise, emotional reassurance, or a stable social life. It does not grow lonely in the human sense. It does not suffer homesickness. It does not need gravity to keep its bones from weakening because it has no bones to weaken. And perhaps most important of all, it can be built for a narrow purpose. That matters more than it first appears. Human beings are wonderfully adaptable, but we are also extremely demanding cargo. A crewed spacecraft is not just carrying people. It is carrying the conditions required to keep people alive. Air circulation, waste processing, food systems, water recycling, heat management, medical care, sleeping arrangements, psychological design, radiation protection, redundancy against failures that would otherwise become fatal. To send humans into deep space is to send a small artificial world. A robotic probe, by contrast, can be far smaller, far lighter, and far less complicated in certain ways. It can be designed to do one thing well: observe, measure, map, transmit, survive as long as possible. It can power down for long intervals. It can wait. It can endure in silence without turning silence into suffering. This is one reason nearly every serious conversation about the farthest reaches of space begins with machines rather than with people. If humanity ever sends something to another star, or even farther, the first real traveler will almost certainly not be a person standing at a window. It will be a machine. Perhaps something tiny. Perhaps something durable and slow. Perhaps something far more autonomous than anything we have built so far. But still, most likely, a machine. And in a way, that is already how our species has begun its relationship with the cosmos. Voyager 1 and Voyager 2 are not conscious, but they are patient. They continue outward long after the human hands that built them have aged. They do not complain. They do not despair. They simply keep going, transmitting when they can, carrying small memories of Earth into a region no living traveler has entered. The rovers on Mars have done the same on a smaller scale. So have our orbiters, landers, and probes across the solar system. Again and again, the machines go first. There is something beautiful in that. They are not us, exactly. But they are our questions given shape and motion. Still, ordinary robots may not be enough for the intergalactic problem. A mission of that scale would not merely need endurance. It would need judgment, adaptation, self-preservation, decision-making in situations no human could respond to in real time. This is where artificial intelligence begins to matter. The farther a spacecraft travels, the longer communication delays become. Even within our own solar system, signals take time. Messages to Mars take minutes. Messages to the outer planets take hours. Across interstellar or intergalactic distances, communication delays become so long that direct control from Earth stops making sense entirely. A mission traveling for centuries or more cannot depend on constant human supervision. It must be able to think, in some sense, for itself. Not necessarily think like a person. That is an important distinction. Artificial intelligence in the context of space travel does not have to be conscious in the science fiction sense to be useful. It simply has to be capable. Capable of diagnosing failures, adapting to changing conditions, preserving the mission, choosing priorities, correcting navigation, allocating energy, managing risk, and continuing meaningful action when the original programmers are long gone. In other words, a truly deep space AI would need to be less like a tool and more like a steward. It would not merely execute commands. It would carry the logic of the mission forward through time. That begins to feel strangely profound. Because once an AI-guided spacecraft travels far enough, and long enough, something subtle changes in the meaning of the journey. The ship is no longer simply a device launched from Earth. It becomes a continuity of intention, a structure that holds purpose even after the civilization that created it may have changed, weakened, or disappeared. In that sense, AI becomes not just an engineering solution, but a kind of cultural memory. A way for a mission to remain itself across spans of time that would otherwise dissolve ordinary control. Of course, this creates its own uncertainties. A system capable of great autonomy must also be trustworthy. That sounds obvious, but it becomes harder the longer you think about it. What does trust even mean across centuries? How does a machine preserve the original spirit of a mission when conditions change? How should it balance caution against progress? What happens when preserving the craft requires choices the original designers never imagined? A short mission can afford relatively simple rules. A mission lasting beyond generations may need deeper adaptability. And deeper adaptability begins to look more and more like something close to agency, even if we are careful not to call it that too quickly. Would that be safe? Would it be wise? Would it remain aligned with human values long after the humans who wrote those values are gone? These are difficult questions even for computers here on Earth, surrounded by infrastructure, updates, oversight, and constant revision. In the cosmic void, such questions would be carried into near-perfect isolation. So robots and AI may solve some of the human problem, but they introduce a new one. They reduce biological fragility, but they increase the importance of long-term system integrity. Instead of asking whether a crew can remain sane and healthy, We begin asking whether an autonomous intelligence can remain coherent and faithful to its purpose across time and distance so vast that no easy correction is possible. And yet, even with that risk, machines still seem better suited than people for the first truly impossible voyages. Because they do not need the universe to feel livable. That may be the deepest advantage of all. A robot does not need home. It does not need seasons, laughter, rain, trees, or a sense that life is unfolding naturally around it. It can function in a place where nothing feels human because it was never human to begin with. That makes it, in some ways, the ideal pioneer of the void. Not because it is nobler than us, but because it is less offended by emptiness. Still, some people will always resist the idea that machines alone should inherit the farthest frontiers. For many, the dream of space is not just knowledge, it is presence. To say that only robots can feel, emotionally, like giving something up. It can feel like admitting that the universe is larger than our bodies can follow. And perhaps that is exactly what it is. But human beings are not always willing to surrender so easily. Which brings us to the most ambitious and unsettling alternative of all, the generation ship. A generation ship tries to solve the lifespan problem in the oldest way human societies know how. If one life is too short, then many lives must be linked together. Instead of imagining a crew that personally completes the journey, it imagines a society that continues it. A moving world. A vessel large enough, stable enough, and self-contained enough to carry not just travelers, but descendants. At first, there is something almost comforting about the idea. If the distance is too great for one lifetime, then perhaps the ship itself becomes the lifetime. A child is born on board, learns the corridors and systems as home, grows into adulthood under artificial skies or carefully lit chambers, has children of their own, teaches them the same story. Generation after generation, the mission continues not because any one person can complete it, but because the society inside the ship agrees to carry it forward. This has the shape of an answer, but it also has the weight of one. Because a generation ship is not just a transportation problem, it is a civilization problem, a political problem, an educational problem, a moral problem, a cultural problem, a psychological problem. It asks not how to keep a few people alive in transit, but how to maintain a functioning society in a sealed environment for longer than most civilizations on Earth have remained unchanged. That is a much harder thing to imagine than engines. A generation ship would need to produce food, recycle water, preserve air, manage waste, sustain energy systems, maintain structure, train new engineers, preserve knowledge, regulate conflict, protect against corruption and instability, and somehow keep the central purpose alive across countless changes in mood, identity, and historical memory. It would not merely carry life. It would have to recreate, in miniature, the conditions of continuity that whole planets struggle to maintain. And all of it would happen inside a machine. What kind of culture would emerge there? Would the people on board still think of themselves as travelers after many generations, or would the ship simply become the world? Would the destination remain real, or would it begin to feel like a myth? A sacred story repeated more out of tradition than living conviction. What happens if one generation decides it no longer consents to the journey? What if factional conflict emerges over resource use, governance, reproduction, or mission goals? What if some people want to preserve the founding purpose while others want to redefine life on board entirely? These questions do not weaken the idea of a generation ship. They reveal what it truly is. Not a vessel, exactly, but a portable society. And portable societies are fragile things. Even on Earth, with forests, oceans, agriculture, trade, migration, vast physical space, and countless layers of external support, civilizations struggle. They rise, fracture, renew themselves, lose memory, gain memory, reform institutions, forget why they built what they built. Now shrink all of that into a closed habitat in deep space, with no wilderness to escape into, no neighboring cultures, no external reserves, and no planetary abundance beneath the ground. The challenge becomes immense. Still, some thinkers argue that generation ships may be more realistic than suspended animation or physics-defying propulsion because they accept the burden of time rather than trying to erase it. They say, in effect, if the universe requires long durations, then let the mission become a long duration. Let time itself be part of the design. There is something deeply human in that response. It is patient, almost agricultural, less like a heroic sprint and more like planting a forest whose shade you will never sit beneath. A generation ship does not promise personal arrival. It promises continuity. And continuity, in the face of cosmic scale, may be one of the few truly honest answers available. But honesty does not make it easy. There is also a more radical possibility, somewhere between robots and generation ships. A ship run mostly by machines, with humans present only in intermittent ways. Perhaps sleeping for long spans if some future form of safe suspended animation becomes possible. Perhaps waking only at intervals. Perhaps living only near the final approach. Or perhaps existing on board mostly as stored information, embryos, preserved genomes, or other forms of potential life rather than continuous waking passengers. These ideas can sound cold at first, but they are attempts to compromise with reality. If conscious human life is too expensive to sustain every moment of the journey, maybe it should not be asked to. Maybe the machines carry the mission most of the way, and the human presence is reduced, protected, delayed, or reintroduced only when conditions make sense. That possibility opens another strange door. Perhaps the best human intergalactic mission would not be fully human during most of its crossing. It might be a hybrid, part archive, part machine, part future society waiting to be born. A traveling seed rather than a traveling city. That idea feels less romantic than a crew at a window, but perhaps more truthful. The farther we push into realistic thinking, the more the universe seems to reward humility over heroics. There is also a philosophical shift hidden inside all these options. Robots, AI, generation ships, sleeping crews, embryo missions, machine-guided arcs. Each of them changes the meaning of exploration. They ask whether the point of traveling is that a particular person arrives, or whether it is enough that intelligence, memory, or life in some form continues onward. They ask whether humanity's future in the cosmos must look like us in the familiar sense, or whether it will gradually become something more distributed, more mediated, more reliant on systems that are not entirely biological. That may be the quietest and most unsettling realization of all. The universe may not invite us to remain exactly as we are. It may invite us only if we are willing to travel through other forms, through machines, through descendants, through long continuity rather than short heroism, through systems able to endure a scale that the ordinary human body and ordinary human lifetime simply cannot. And yet there is no reason to feel despair in that, because the desire behind all of these ideas is still recognizably human. The desire to know, to continue, to send something of ourselves farther than our bodies can go, to refuse the prison of one lifetime, not by denying mortality, but by extending intention across time in new ways. In a sense, we already do this on a smaller scale. We write books for readers we will never meet. We plant trees whose mature shape we will never see. We build institutions that outlast us. We raise children who carry forward thoughts, habits, and values we only partly control. Human life has always extended itself beyond the individual through memory, culture, tools, and inheritance. Intergalactic travel simply stretches that familiar pattern to a scale so large that it becomes unmistakable. Maybe that is why the generation ship idea feels both strange and deeply old at the same time. It is not just about crossing space. It is about turning continuity itself into a method of travel. So could robots, AI, or generation ships do better? In some ways, yes. Robots can endure what would exhaust us. AI can manage the long silence better than direct control from Earth ever could. Generation ships can accept time rather than trying to defeat it. Hybrid missions may blend these strengths in ways we cannot yet fully imagine. If the question is which kind of traveler is most compatible with the brutal scale of the cosmic void, then the answer is probably not a conventional human crew. The void seems to favor patience over presence. It favors endurance over immediacy. It favors systems that can continue without needing the universe to feel kind. But whether those alternatives are better in the deeper sense is harder to say. A robot may survive the journey more easily than a person, but does that satisfy the old human longing to arrive? A generation ship may carry life forward, but at the cost of turning a mission into a civilization with all the risks that implies. An AI steward may preserve the logic of the voyage, but what does it mean for a human dream to be carried mostly by a non-human mind? These are not reasons to reject the possibilities. They are reasons to take them seriously. Because the farther we imagine going, the more the universe insists that we ask not only what can travel, but what should. If this quiet part of the journey has settled into your thoughts tonight, you can softly like the channel, subscribe, or leave a comment with the future that feels most believable to you. A machine alone in the dark. A ship full of descendants. An AI guardian carrying a mission across ages. Or something stranger that humanity has not yet learned how to imagine clearly. For me, what lingers is this: that the cosmic void may not be crossed by the kind of traveler our stories first taught us to expect. Not the heroic individual standing at the front window of a ship, but something calmer, more patient, more distributed across time. A machine carrying memory. A society carrying purpose. An intelligence carrying instructions across ages too long for any one body to endure. And perhaps that is not a defeat of the human dream at all. Perhaps it is the dream maturing, becoming quiet enough to admit what the universe is actually asking. Not speed alone, not courage alone, but continuity, patience, and a form of travel large enough to survive the dark. Part 9. The expanding universe makes everything worse. There is something almost cruel about distance in the universe. Just when the numbers have already become too large to feel human, just when the empty space between galaxies has already begun to seem severe enough, another truth quietly enters the room and makes everything harder. Not louder, not more dramatic, just harder in a deeper, colder way. Because the universe is not sitting still while you try to cross it. The space between galaxies is not a fixed stage with bright islands placed neatly across a black background. It is changing, stretching, unfolding. And that means a distant destination is not always just far away. Sometimes it is becoming more far away while you think about reaching it. That is one of the strangest and most unsettling ideas in modern cosmology. If you wanted to cross a desert, it would be bad enough if the desert were immense. But imagine walking toward the other side while the desert itself slowly widened beneath your feet. Imagine trying to cross an ocean while the shore ahead drifted away, not because of wind or current, but because the water itself was expanding. That is closer to what the large-scale universe is doing. And tonight, that quiet fact changes the emotional shape of the journey. Because until now, it has been possible to imagine the cosmic void as a terrible but stable crossing, a long route, a harsh environment, a place where a ship might fail for reasons of energy, time, biology, or endurance. But now the problem becomes even stranger. The road itself is changing. The map is not fixed. The distance to some galaxies is not merely immense. It is actively increasing as the universe expands. If these slow explorations help calm your mind at night, you can gently like the channel, subscribe, or leave a comment about which idea feels the most difficult to picture. For many people, it is not black holes or explosions. It is this quiet thought that space itself can stretch. To understand why the expanding universe makes everything worse, it helps to begin with an ordinary instinct. We tend to imagine space as a kind of container, a giant dark room, perhaps unimaginably large, but still basically a room. Galaxies are inside it, stars are inside it, we are inside it, and if something moves farther away, we assume it is moving through that room the way a boat moves through water or a plane moves through air. Something goes from one place to another across a stable background. That picture feels natural. It is also incomplete. On the largest scales, the universe does not behave like objects moving through a fixed empty container. Instead, the structure of space itself changes over time. Distances between faraway galaxies increase not only because galaxies may move in the ordinary sense, but because the very fabric of the universe is expanding. This is the part that can make the mind go quiet for a moment. Because space is not just where things are, it is part of what changes. A useful image, though not a perfect one, is to imagine points drawn on the surface of an inflating balloon. As the balloon expands, the points move farther apart, even if they are not crawling across the rubber themselves. The surface between them stretches. The distance grows because the background grows. Now, the universe is not literally a balloon, and it is not expanding into some outer room the way a balloon expands into air. That picture can mislead if taken too far. But for calm intuition, it helps. The main idea is simple. Galaxies on large scales are being carried farther apart because space itself is stretching. And this stretching has consequences. The first consequence is psychological. It means that when you look out into the deep universe, you are not looking at a static arrangement of distant lights. You are looking at a history of separation. The farther away the galaxy, in general, the more the expansion of the universe matters to its relationship with us. This was one of the great discoveries of 20th century astronomy. When astronomers studied the light from distant galaxies, they found that many of them were redshifted. Their light had been stretched toward longer, redder wavelengths. One of the main reasons for this, on cosmological scales, is that space expanded while the light was traveling. The light itself was pulled longer by the changing universe. That is an extraordinary thought. A photon can begin its journey in one cosmic era and arrive in another, carrying inside its stretched wavelength the quiet record that the universe changed while it was in transit. And if space can stretch light, then it can certainly stretch journeys. This is where the dream of crossing the void begins to feel even more difficult than before. Because in a static universe, a distant galaxy would at least remain at a fairly stable large-scale separation unless something else disturbed the situation. The destination would be far, yes, but the farness would not be growing simply because reality itself was changing underneath the root. But that is not our universe. Our universe expands. And not only that, the expansion of the universe appears to be accelerating. On the largest scales, distant galaxies are not just moving apart. The rate at which that separation grows is shaped by the strange large-scale behavior of the cosmos, often associated with what we call dark energy. We do not fully understand dark energy in the deepest sense. It remains one of the biggest mysteries in physics. But its observed effect is enough to matter profoundly here. The large-scale universe is not merely expanding. It is doing so in a way that makes the remote future even more lonely. That has direct consequences for travel. Because if a galaxy is far enough away, the expanding universe is not a small background detail. It becomes part of the obstacle. You are not simply crossing a fixed gulf. You are crossing a gulf whose geometry is evolving. There is an important subtlety here, and it helps preserve the beauty of the truth rather than turning it into confusion. Not everything in the universe is being torn apart by expansion in the same way. Gravity still matters. Strongly bound systems resist the expansion of the universe on local scales. The Earth does not drift away from the Sun because cosmic expansion is too weak to overcome the local gravitational bond. The solar system stays together. The Milky Way stays together. Even groups and clusters of galaxies can remain gravitationally bound, resisting the tendency of large-scale space to stretch them apart. This is why your room is not expanding. Your body is not expanding. Our galaxy is not dissolving because of cosmic expansion. Local structure holds. But beyond those local bindings, across the largest scales, the expansion wins. That distinction matters because it means not every cosmic destination is equally doomed. Andromeda, for example, is not being carried away from us by cosmic expansion in the way distant galaxies are. It is actually moving toward the Milky Way. Gravity between our galaxies, both part of the local group, dominates the relationship. In several billion years, the Milky Way and Andromeda are expected to merge. So Andromeda is a wonderful exception. It reminds us that local gravity can overrule the broader expansion. But exceptions do not cancel the rule. Beyond our gravitational neighborhood, more distant galaxies generally recede as the universe expands. The farther out you go, the more important that recession becomes. At great enough distances, galaxies move away not because they are blasting through space like bullets, but because space between us and them is expanding. This creates one of the strangest features of the observable universe. There are galaxies so distant that the space between us and them expands in such a way that they recede effectively faster than light in the cosmological sense. That sounds like a violation of relativity at first, but it is not, because relativity limits how objects move through local space. It does not forbid space itself from expanding. Again, this is one of those moments where the universe refuses to fit comfortably inside ordinary language. And for travel, it introduces a chilling possibility. There are regions of the universe that are not merely difficult to reach. They are fundamentally slipping away from causal contact. Light emitted from some very distant places now may never reach us in the future. Not because light has become weak, and not because someone blocked the path, but because the intervening space expands too relentlessly. This brings us to the idea of a cosmic horizon. A horizon is a beautiful word because it feels familiar. On Earth, the horizon is just the limit of what you can see before the curvature of the world hides the rest. It feels soft, almost poetic. But in cosmology, a horizon can mean something far more profound. It can mark a limit beyond which events may never influence you because the expansion of the universe prevents signals from ever bridging the gap. In other words, there are places from which the future is, in a practical sense, sealed away. That is one of the most haunting facts in modern science. The universe is not only large, it is dynamically separating itself. And if you imagine trying to cross the cosmic void in such a universe, the problem becomes more than just engineering. Some destinations are receding into a kind of permanent remoteness. The longer you wait, the worse it gets. The future is not neutral. Delay has cosmological consequences. This is another way the expanding universe makes everything worse. It turns distance into a race against time, at least in principle. Not because you could build a ship tomorrow and solve it, but because the structure of the cosmos itself is evolving in a direction that increases isolation. There is something almost sorrowful in that. It means the universe of the far future will not look as richly connected as the one we see now. Over immense spans of time, distant galaxies will drift farther away, their light stretched thinner and dimmer. In the truly deep future, observers in our local region may see a much emptier sky than we do now. The broader cosmic web, so full of distant structure to our telescopes today, will slowly fade beyond reach. The universe will not necessarily become physically emptier nearby, but it will become observationally lonelier. The great islands beyond our neighborhood will retreat into darkness. That thought alone is enough to change how one sees the night sky. Because every distant galaxy visible to us now is part of a temporary age of access. We live in a time when the universe still reveals much of its large-scale structure to us. The cosmic expansion has not yet hidden everything behind an unreachable horizon. We are, in a quiet sense, lucky. We live early enough to still see. And that makes the dream of crossing those distances feel even stranger. Not only are the galaxies far away, not only is the void harsh, not only is speed too slow and energy too costly and human life too brief, but the universe itself is slowly reducing the intimacy of its own structure. It is widening the separations, letting the islands drift farther apart. Of course, this should be handled gently, because not every distant object is immediately becoming impossible in a simple everyday sense. The universe is subtle. Nearby bound systems remain bound. Local motions matter. Paths depend on scale. But the deeper lesson remains solid. Cosmic expansion is not your friend if your dream is to casually move from one remote galaxy to another. It increases the seriousness of the problem. A useful way to feel this, without drowning in equations, is to imagine a long walkway that slowly extends while you are trying to cross it. If you can walk much faster than it extends, you still make progress. If you walk only slightly faster, the journey grows exhausting. If the walkway extends as fast as you move, you never truly get closer. And if it extends faster than you move, the destination recedes forever. That is not a perfect image for cosmology, but it captures the emotional structure of the problem. For some destinations, the universe is not merely challenging you to endure the crossing. It is quietly asking whether crossing is still meaningful at all. There is also a philosophical twist hidden inside this. Expansion changes what we mean by the same place. If a galaxy is billions of light years away and the universe continues evolving while you travel, then the destination you imagined at departure is not really waiting untouched at arrival. Stars evolve, orbits change, galaxies collide, merge, age, and transform. New stars are born. Others die. Black holes feed. Dust shifts. The universe is not a museum. It is a process. So even if you could cross enormous distances, the target would not be frozen in time waiting politely for your arrival. This is something we already know from light. We see distant galaxies as they once were. A galaxy a billion light years away appears to us as it was a billion years ago. That means deep observation is already time travel in one direction. But travel would intensify this truth. The more distant the journey, the more impossible it becomes to separate where from when. And that makes the voyage feel almost dreamlike. You are not just trying to reach another place. You are trying to intersect another unfolding history while your own history continues elsewhere. In that sense, the expanding universe does not simply increase physical difficulty. It destabilizes the old fantasy of clean arrival. The farther out you go, the less the destination resembles a waiting point on a map and the more it resembles a moving condition inside a changing cosmos. This also helps explain why cosmology often feels both beautiful and sad. Beauty, because the universe is so much richer than a static machine. Sadness, because richness includes separation. Growth includes loss. Expansion includes a thinning of connection. The same process that gives the cosmos its grand evolving form also ensures that parts of it will become more remote, more unreachable, and eventually, in some sense, more alone. And that loneliness is not dramatic. It is patient. The universe does not slam doors. It widens halls until voices can no longer cross them. If a civilization in the far future looked up from somewhere inside our local group, after billions upon billions of years, it might know much less about the broader universe than we do now. The distant galaxies that taught us about expansion and the Big Bang might be gone from view, not because they ceased to exist, but because their light would no longer reach that future observer in a useful way. The evidence of the wider cosmos would fade. The sky would become more provincial, more local, more silent. That is one of the strangest possibilities in all of science. There may be truths about the universe that are visible to us now, but would be hidden from intelligent beings born too late. We live in an era when the cosmos is still speaking across immense distances. And that makes the dream of traveling those distances feel touched by urgency, even if only in thought. Not an urgency of panic, but of perspective. A reminder that access is temporary. The great map of visible galaxies is not guaranteed forever. So yes, the expanding universe makes everything worse. It worsens the problem of distance by making distance dynamic. It worsens the problem of travel by turning some destinations into moving targets. It worsens the problem of waiting by ensuring that delay is not neutral. It worsens the emotional burden by showing that isolation is not only spatial, but historical. The farther the future unfolds, the more separated the grand structures of the cosmos become. And yet, oddly enough, there is something peaceful in understanding this. Because once you accept that the universe is not built for convenience, something inside the mind stops demanding that it should be. The cosmos does not owe us stable roads between galaxies. It does not owe us easy horizons or timeless destinations. It simply unfolds according to deeper laws, and those laws produce a reality both harsher and more beautiful than our early intuitions ever suggested. The galaxies are not just far. They are part of an expanding story. The void is not just empty. It is being stretched. And the night sky is not just a ceiling of remote lights. It is a temporary window into a universe that is already, slowly, pulling parts of itself away from one another. If this part of the journey has made the cosmos feel larger in a new way tonight, you can softly subscribe, leave a like, or share in the comments the idea that stays with you most. For some, it is the fact that Andromeda is an exception, still falling toward us while the larger universe expands away. For others, it is the thought that there are galaxies whose future light may never arrive here at all. For me, it may be this: that the universe does not merely contain distance. It manufactures it, quietly, continually, across ages so large they make even galaxies feel like drifting thoughts. And once you truly feel that, crossing the cosmic void stops sounding like a hard journey through a fixed darkness. It starts sounding like an attempt to travel across a darkness that is still being made. Part 10. Will crossing the cosmic void ever be possible? After everything we have seen, there is a natural temptation to answer the question quickly. No. The distances are too large. The speeds are too small. The energy demands are too severe. The human body is too fragile. The hidden dangers of radiation, dust, and long exposure are too difficult to ignore. And beyond all of that, the universe itself is expanding, slowly widening the great separations between galaxies. If you gather all of those truths together and hold them in one place, the simplest answer seems obvious. No. Crossing the cosmic void is too hard, too far, too expensive, too slow, too late. And yet the universe has a way of making quick answers feel incomplete. Because impossibility is a slippery word. Sometimes it means a thing can never happen under any laws of nature. Sometimes it only means that the thing is far beyond the reach of the tools, timescales, and imagination we currently possess. Sometimes impossible really means not for us. Not like this. Not now. Not by any civilization that still resembles the one we know. And that is where the final question becomes softer and more interesting. Not whether crossing the cosmic void is easy. It is not. Not whether it is realistic for modern humanity. It is not. But whether it belongs in the deeper category of forever impossible, or whether it belongs to that strange borderland where the universe says, not forbidden, only costly beyond your current scale. Tonight, the journey comes to rest in that uncertainty. Because after all the numbers, all the hazards, all the hard physics and quiet limitations, what remains is something more reflective. What kind of future would it take to even attempt such a crossing? What would have to change about our technology, our timescales, our idea of travel, perhaps even our idea of ourselves? And if the answer is not a simple yes or no, what does that ambiguity reveal about the cosmos, and about us? If these slow explorations help you wind down at night, you can gently like the channel, subscribe, or leave a comment about what you think the far future of space travel looks like. A machine in the dark, a city-sized ship, a civilization that learns patience on scales we can barely imagine. It is always interesting to see which version of the future feels most real to different people. To begin, it helps to make one careful distinction. Crossing the cosmic void is not forbidden in the way faster than light travel appears to be forbidden by our current understanding of physics. As far as we know, nothing with mass can simply outrun light through space. That seems to be one of the deepest limits built into reality. So if someone asks whether we can cross to another galaxy quickly, in the everyday sense of quickly, the answer is almost certainly no. Not by ordinary motion. Not by anything we currently understand. But crossing eventually is a different question. If the laws of physics allow matter and energy to move through space at sublight speeds, then in principle distance can be crossed. The problem is that principle and practice are separated by an enormous gulf of their own. In principle, you can walk across a continent. In practice, mountains, weather, hunger, age, and time transform that principle into something very different. In principle, a spacecraft could move toward another galaxy. In practice, the journey becomes so demanding that the phrase, in principle, starts to sound almost like a joke. Still, it matters that the laws do not seem to forbid the movement itself. That means the real obstacle may not be cosmic law alone. It may be scale, duration, engineering maturity, civilizational patience. The kind of patience that human beings have rarely demonstrated, because our projects usually live inside the boundaries of careers, governments, lifetimes, and markets. We build for years, perhaps decades. We plan for generations only in the vaguest sense. But intergalactic travel would laugh gently at all of those horizons. It would ask for thinking so extended that the word project no longer fits. Perhaps that is the first thing that would have to change. Not the engines. Not at first. The timescale of thought. A civilization that seriously considered crossing the space between galaxies could not behave like one thinking in election cycles, product cycles, or even the lifetimes of institutions. It would have to think in layers of continuity far deeper than most of human history has ever demanded. It would need to treat time not as an enemy to compress, but as an environment to design for. That alone makes the idea feel almost alien. Because modern life conditions us to value speed, iteration, rapid delivery, visible results. We celebrate acceleration. We admire disruption. We often treat patience as a temporary inconvenience rather than as a serious power. But the cosmic void does not yield to that mentality. It does not care how badly you want the answer faster. It rewards endurance, not urgency. It favors systems that can continue when the original builders are gone. In that sense, the first requirement for crossing the void may be cultural rather than technical. A civilization mature enough to build for futures it will never personally see. And even then, technology would still need to become something very different from what it is now. Today, most of our machines are children of abundance. They rely on complex supply chains, specialized maintenance, replacements, updates, repairs, and a surrounding industrial world ready to support them. Even our best spacecraft are remarkable partly because they endure beyond the conditions under which ordinary machines would fail. But when a probe lasts decades, we call it extraordinary. Intergalactic travel would ask for systems lasting far beyond that. Not years. Not even a human lifetime. Potentially centuries or much more, depending on the method. So the technologies that might matter most are not only high-speed engines, but long-lived systems, self-repairing materials, closed-loop ecological design, ultra-durable energy production, autonomous maintenance. Redundant architecture that does not merely survive failure, but slowly learns how to root around it. Manufacturing systems compact enough to operate on board. Intelligence capable of preserving mission continuity without constant oversight. Storage methods for knowledge and memory that do not decay into nonsense across deep time. Those kinds of technologies already sound less like ordinary spacecraft engineering and more like the design of portable worlds. And perhaps that is exactly what they would need to be. The most realistic path toward something like intergalactic reach may not be a sleek vessel in the old science fiction sense. It may be something slower, stranger, and more self-contained. Less like a ship and more like a migrating habitat. Less like a journey and more like a continuity system moving through the dark. That thought can feel disappointing at first, especially if what you wanted was the romance of fast travel. But there is another way to see it. Perhaps maturity in the cosmos means giving up the fantasy that every great distance must be conquered dramatically. Perhaps the deepest form of travel is not speed, but persistence. There are, of course, more speculative possibilities. People often wonder whether some future physics breakthrough could change everything. Wormholes, warp drives, bending space itself. Shortcuts through geometry rather than motion through ordinary distance. These ideas are fascinating, and some have roots in real theoretical physics, at least as mathematical possibilities. General relativity allows strange structures in principle. Space-time is richer and stranger than common sense ever guessed. So it is understandable that the mind reaches for these ideas when ordinary travel becomes unbearable to contemplate. But there is an important difference between mathematical permission and physical practicality. A theory may allow a certain kind of geometry under extreme conditions without giving us any realistic way to create, stabilize, or use it. A concept may be beautiful on paper and still remain forever unreachable in practice because it requires forms of matter, energy, or control beyond anything the universe seems willing to hand us. So while it is wise to leave a little room for humility, because science has surprised us before, it is also wise not to treat speculative escape hatches as if they are already roads waiting to be paved. The honest answer is that we do not know. There may be aspects of physics we have not yet understood. There may be future revolutions in energy, matter, computation, or space-time engineering that would seem magical from where we stand now. But there is a difference between open possibility and grounded expectation. And if we stay grounded, then crossing the cosmic void still looks unimaginably hard. Perhaps that is the most truthful sentence in the whole story. Not certainly impossible. Not meaningfully possible for us. Unimaginably hard. And even that phrase may not fully capture it. Because to cross between galaxies is not merely to travel far. It is to fight against almost every condition that makes travel familiar. On Earth, journeys are supported by worlds. In the void, the traveler must carry the world with them. On Earth, generations inherit land, climate, and ecology. In deep space, generations would inherit systems that must remain artificial without pause. On Earth, a traveler moves through landscapes that answer the body. In the cosmic void, the body receives almost no answer back. So perhaps the better question is not whether a crossing is possible in the abstract, but what kind of being could complete it? A modern human crew? Almost certainly not. A robotic intelligence built for astonishing patience? More plausible. A generation ship carrying descendants across ages? Perhaps, but at a cost so large it would transform the meaning of the mission. A hybrid form of life and machine? Maybe. A civilization so ancient and stable that our categories of travel no longer fit its capabilities? That becomes harder to dismiss, simply because the timescales begin to outrun our imagination. And this is where the question opens into something bigger than humanity alone. If intelligent life exists elsewhere in the universe, and if some of it is much older than we are, what might its relationship to cosmic distance look like? A civilization only a few hundred years more advanced than us would still likely face many of the same barriers. But what about 100,000 years older? A million? 10 million? At those scales, the conversation starts to feel almost theological, not because it becomes supernatural, but because the gap in perspective grows so enormous that prediction becomes nearly meaningless. An old enough civilization might not build ships the way we think of ships. It might preserve intelligence in forms we would not recognize as biological. It might move slowly on purpose, sending seeds of itself into the dark with no expectation of immediate reward. It might accept travel times that feel impossible to us because its notion of continuity no longer depends on the individual body. It might use matter and energy with efficiencies we can barely picture. Or it might conclude, after all its wisdom, that intergalactic travel is a poor bargain and turn inward instead, preferring local richness over distant ambition. That last possibility is worth lingering on, because one hidden assumption beneath many conversations about space travel is that farther must always mean better. That if a thing can be reached, then intelligence will naturally wish to reach it. But that may be a very young species' way of thinking. There may come a point in a civilization's development where the desire to expand outward is balanced, or even surpassed, by the desire to deepen inward. To build not a larger map, but a richer home. If that sounds like surrender, perhaps it is not. Perhaps it is simply wisdom. After all, crossing the cosmic void is not the only way to encounter wonder. The universe offers endless depth even locally. A single galaxy contains hundreds of billions of stars. A single planetary system can hold lifetimes of discovery. A single conscious mind can spend years contemplating truths already present in one patch of sky. Scale is not only horizontal, it is vertical too. The near can be as inexhaustible as the far if attention becomes fine enough. And yet, the human spirit is not wrong to keep asking. There is dignity in wanting to know whether the great dark can ever be crossed. Because the question is larger than transportation. It is about the relationship between finite beings and an apparently unending universe. It is about whether intelligence must remain provincial forever, bound to its local island of stars, or whether there are roads, however slow and strange, by which the islands may someday be connected by intention. Maybe the answer is that connection will happen, but not in the form we first imagined. Not heroic crews leaping between galaxies in bright ships, but signals, archives, machines, and descendants. Slow emissaries crossing darkness over spans that make individuals irrelevant but do not make meaning irrelevant. That possibility changes the emotional tone of the question. Will crossing the cosmic void ever be possible? For a person, in the familiar sense, perhaps not. For intelligence, memory, or life extended through systems larger than a single lifetime, perhaps yes. And if that is true, then the journey belongs less to adventure than to inheritance, less to speed than to continuity, less to the triumph of one moment than to the preservation of purpose across many moments no one living now will ever see. There is something strangely calming in that, because it removes the pressure to solve the universe on human emotional terms. It allows the cosmos to remain large without turning that largeness into defeat. We do not need the answer to be personally reachable for it to be meaningful. There is still beauty in knowing the shape of the challenge, even if the challenge outruns us. In some ways, that is what science has always taught most gently. Not that the universe exists to flatter our scale, but that understanding it can still enlarge us, even when we remain physically small inside it. When you realize that another galaxy is not just far, but millions of years far even for light, something in you changes. When you realize that the space between galaxies is not empty in the easy sense, but hostile in quiet ways, something in you becomes more precise. When you realize that the universe is expanding, and that some parts of it are becoming more remote with time, something in you learns to respect the deep patience of reality. And perhaps that respect is already a kind of arrival. Not arrival at another galaxy, but arrival at a more truthful relationship with the one universe we already inhabit. There is also a softer personal lesson hidden here. Most of life is lived at scales we can touch. A room, a street, a family, a season, a city at night, a body getting tired, a mind trying to rest. Against all of that, the cosmic void can seem almost absurdly large, so large that it risks turning into abstraction. But if you sit with it long enough, the lesson is not that your life is meaningless beside such scale. The lesson is that scale changes the flavor of meaning. The universe does not make small things worthless. It makes them delicate. A warm house on a cool night, a conversation, a breath of ordinary air, the sight of clouds, the sound of rain, the comfort of being held by gravity and atmosphere without ever asking them to stay. Once you really understand how hostile the dark between galaxies would be, these ordinary things stop feeling ordinary. They begin to look like luxuries granted by an astonishingly specific home. So maybe that is where the final answer settles. Crossing the cosmic void may someday be possible for some form of traveler, under conditions far beyond what we can currently build, perhaps by methods we only dimly foresee. It may never be possible in the fast, personal, human-centered way our younger imaginations prefer. It may belong instead to machines, descendants, or civilizations patient enough to treat millennia as manageable. Or perhaps the universe will always keep that particular road too expensive to travel in any meaningful way. We do not yet know. But the uncertainty itself is beautiful, because it leaves room for humility without demanding despair. It lets us admit the severity of the cosmos without pretending that every mystery must be closed tonight. It allows science to remain what it often is at its best, not a machine for flattening wonder, but a way of carrying wonder more honestly. If this long quiet journey through the cosmic void has kept you company tonight, you can softly leave a like, subscribe for more slow explorations, or share in the comments what answer feels truest to you. Not whether the journey is easy, because it is not, but whether you think the future belongs to human crews, patient machines, or some form of life we have not yet learned how to imagine. For me, what lingers most is this. The universe is not telling us a simple no. It is telling us that every great distance has a price, and that some prices are so high they force intelligence to grow before it can pay them. Maybe crossing between galaxies is not the next step for a young civilization. Maybe it is the kind of step that can only be taken after a species has learned patience, continuity, humility, and a deeper relationship with time than we currently possess. And until then, perhaps the most meaningful thing we can do is look outward clearly, understand the scale honestly, and let that honesty change the way we feel about home. Because in the end, the cosmic void does not only ask whether we can cross it, it asks what kind of beings we would need to become before such a crossing would mean anything at all. And for now, under a quiet sky, that question may be enough.